Welcome you all to the ICRA 2021 workshop on robot assistant systems for medical training. I'm Tilina from Imperial College London, and I'm one of the organizers of this workshop. I would like to introduce our amazing team. We have Trish from Imperial College London, and we have Fumia from Cambridge. I don't know whether he's here. Paula from Oxford, and we have Min from Xi'an Zedong University from China, and we have Jacob from Imperial. Jacob. We have Florence from Imperial and Liang from Oxford and Luca from Cambridge. And we have Raymond from Cambridge. And finally, we have Sibyl from Imperial College London. I know this has been a strange time for most of us due to COVID and travel restriction around the world. But despite all these odds, I'm really happy that we are gathered here to discuss and contribute to science, specifically in medical training, and how robotics can help to improve the medical training. So we have a really exciting full workshop agenda with number of talks and technical clinical talks with the experts in the field. I warmly welcome all the keynote speakers, clinical speakers, and technical speakers for joining with us and share their knowledge and research with us today. Also, I would like to welcome all the post presenters to this workshop. And in addition, we have a lot of workshop participants joining around the world. It is my pleasure to welcome you all to this workshop. By looking at the presentation titles, you can go through the website and abstract. So I'm sure this will be an exciting workshop for everyone. This workshop organized as a part of an effort from a project called Robopatient, which is funded by PRC. Where Imperial College London, University of Oxford, and University of Cambridge are partners. So in that context, I would like to invite Dr. Shashantan Anayakar, Director of MOP Lab, Imperial College London, to give a word of introduction about this workshop. Trish.
Yes, thank you very much, Tilina, for this. Let me try to share my screen. Do you see my slide?
Yeah, I can see it.
Yes. As Tilina said, this workshop is organized as part of the Robopatient outreach activities. So to give an context, the US healthcare simulation market alone is shown in this graph. So it started about 2014, $325 million market, and then it is growing exponentially. And then the global medical simulation market size was valued at 1.36 billion in 2017, which is roughly 3 times the US market. And it is estimated to expand at a compound annual growth rate of 16.3% over the forecast period. So various intelligence agencies have varying forecasts, so it varies from about 14% to 17% growth rate. So if we look at what is growing, we can see hardware anatomical models and web-based and software-based simulators, simulation training. So it is a combination of hardware and software that is developing, and then it is going towards more like augmented reality solutions in the future. So the Robopatient team I'm the director and the principal investigator of the Robopatient research team, which is funded by the UK Engineering and Physical Sciences Research Council. And then I'm joined by my colleagues Mazda Gajari, Neera Van Salk, Simon Lucian from Oxford, and Fumia Ada from Cambridge. And then 2 postdocs from my lab, Florence Leong, Tilina Lalit Ratna, they are postdocs. And then Liang He was a PhD student in my lab, and then now he's a postdoc at University of Oxford. And then Jacob Tang from Imperial, and Sibyl Perron, she is also from Imperial. She's an undergraduate student, but she's very active in research. And Luca Simica, he was a postdoc at University of Cambridge. Now he is going to Harvard to continue his independent research. Um, so this is the idea of the Robopatient project. So we have a robotic face that can camouflage or change configurations itself to camouflage patients from different ethnic conditions, right? And gender. So white male, white female, black male, black female, Asian male, Asian female. And then the idea is to allow medical students to examine for example, the abdomen of a patient to locate some kind of a painful location. And then when they exert forces, palpation forces, at some point when they are near the pain point, the robotic face will give a pain expression. So these pain expressions have a uniform map from the force to the pain, but when they are elicited from different facial backgrounds, for example, black male versus a white male, the perceived pain depends on our own ethnic and gender background. So the idea is to make interventions such as force display or stress display, which are gender and ethnic neutral, together with the face, so that we can normalize our perception of pain across different ethnic and gender backgrounds. So this will hopefully give a platform, augmented reality platform for medical students to normalize their biases towards various gender and ethnic backgrounds of patients that otherwise will take a long time to learn through real patients when they graduate. So this is what we are doing in the Robopatient project. So there are so many other work going on in this field. So today's objective is to see, listen to medical practitioners and roboticists on the other hand. So this workshop is unique in that sense. We are bringing clinicians and engineers together to think about what is needed in the clinical practice, and then what roboticists can do to help that and to contribute and fill gaps. So hopefully our community will engage actively in the discussions and then contribute to expand this field so that we will design and produce useful medical robotic medical robotic solutions to assist our doctors. Thank you very much.
Yeah, thanks a lot, Trish, for that quick but informative introduction. I hope you can understand what's our motivation behind this workshop and then our background information about this workshop. So without further ado, I think we can now move into the main workshop. We have like another 6 or 7 minutes. But before that, I would like to remind you few housekeeping items that we would like you to pay attention during the workshop. During the workshop, please try to keep your microphone muted unless you are presenting or asking a question, and also make sure to mute or silent your mobile phones or any mobile devices during the workshop. And also, we encourage a question to be asked throughout the workshop, but we may not be able to accommodate all the questions given the time limitation and also the number of participants attend in this workshop. Therefore, if you have any question for the speakers, please send your question in chat, and the respective chairs will deliver your question to the speakers, and it will be presented in one of those ideas and sessions. Those are the background information related to the workshop, and I want to tell you that this workshop is being broadcast live by YouTube. So those who are interested in YouTube link, so you can post your YouTube link in the social network if you want. Yeah, so I think if we can move to the main workshop. Jacob, what do you think? Like, Can we?
Yeah. Thanks, Lena. Good morning, guys. Thanks again for joining our workshop. Our first guest speaker would be Professor Hongliang Ren from the Chinese University of Hong Kong. He'll be presenting on the topic of surgical robotics. I will hand over to Professor Ren.
We cannot hear him.
Hello, can you hear me?
Yeah, I can hear you now. Thanks.
I'm trying to bring up my video. Okay, I got it. All right. Thank you, Jacob, for the nice introduction, and thanks the workshop organizers to bring up the workshop so that we can share some of the experience. And also today, we're going to mainly focus on how to enhance the surgical training. And in order to enhance the surgical training, we already have a lot of experience in developing surgical robotic system. So today, we'd like to take this opportunity to share our recent development, particularly in terms of the tele-robotic system development, in order to generate the motions that are easier to learn by the operators. And at the same time, from the learning point of view, we also want to introduce motion understanding and artificial intelligence, and also other related technology towards augmented minimally invasive procedures. So, without further ado, I will go ahead and introduce a little bit the motivation behind this. We have seen a lot of surgical robotic systems nowadays. A majority of them are taking the format of a master-slave teleoperation. So as we can see, it is essentially human in the loop. We can see the human operators and human assistants, and also the patient. They are all humans. And it's very important for the surgical team, especially for the main operator, we say the master, to learn how to operate the surgical robotic system, the machine. And especially when we're interacting with a lot of tissue, organs, which have significant mismatch in terms of geometry, in terms of mechanical properties. And this is a significantly contact-rich environment. So we know that the Vinci robot, which is very popular, and it has been very intuitive. It's produced by Intuitive Surgical. I guess that is one of the original motivation to have the name, to make it more intuitive in terms of the operation and learning. So we are thinking some of the additional questions along the way. So nowadays we have more and more specialized procedures, for example, transoral, transnasal, transurethral, different very specialized procedures. So can we develop the robot that are more specialized and easy to learn? Meanwhile, we can have sufficient automatic situation awareness and also the intuitive training along with the development process. So today we would like to share some of our recent development in this perspective. So particularly for some of the transoral procedures, transcranial procedures, and also the related situation awareness, some of the intelligence, understanding, emotion understanding based on the image feedback from the surgical scenario. And so we're going to share our motivations, why we are doing that, and also what is the current status, what is the the current system development, what we can do mostly by the demonstrations instead of technical details. So, so we understand that we have a lot of master-slave system in surgical robotics system development. And so in our earlier development, we mainly focus on the slave development. So here we show a few examples as for those people who are not working in this field. We have introduced the concentric tube continuum robot. Some of the principles, especially the continuum tube constraint into a parallel continuum mechanism development. And based on that, we have developed quite a few different slave systems, as we can see the demonstrations in the future slides. And meanwhile, we can see the different master system and master devices we utilize in order to have the teleoperation. So this is one of the very popular devices we see, geometrical touch, which is the current name. And they have a previous name, Omni, Phantom, or some other names. They all share similar articulated serial arm-like structure, which is the kinematic chain configuration, which is the serial kinematic chain over here. And when we are building up the system, we mainly focus on the slave system development. Well, in terms of the master, we also try a few different options. Along the way, we have seen that we can also involve so-called similar kinematic chain to the slave side. In that case, we can make the teleoperation and also make the learning curve shorter, make the teleoperation much easier. So let's take a look at a couple of examples. We have seen, this is the current setup. We can see the images. We're going to play the video very soon. This is the master devices over here. We attach a gripper, which can remotely control the patient side instrument, which is the parallel continuum manipulator right over here. And this parallel continuum manipulator essentially can be approximated as 3 individual parallel kinematic chain. Each one of them has a prismatic, revolute, and spherical joint along the way. So now let's take a look at the video demonstration. Especially you can see it's very difficult for the operator trying to figure out how to manipulate the tissue. It takes quite a lot of time and effort to do the manipulation and to learn from the kinematics. In terms of development, in order to match the motion from the serial articulated kinematic chain to the parallel one, we also need to derive the inverse kinematics. And for the master and slave, and I need to do a lot of numerical calculation. So that takes a lot of effort. So after that, we also need to have significant amount of training to the operators. So based on that observation, we will have to push this one step further. Instead of using the commercially available articulated master device, so we built up our own master system, which essentially mimics the kinematic chain of the slave side or patient side devices, which is also sort of parallel configurations. And the mechanical setup is shown over here in this picture. So as you can see that this is a parallel structure approximated at 3 PRIs, and here we build up a similar 3 PRIs kinematic mechanism, and we incorporate the displacement sensor to pick up the signal so that we can measure the displacement for each individual kinematic chain. In terms of control and teleoperation, it's very straightforward, and we just map each individual kinematic chain directly from the master side to the slave side, just a little bit scaling factors. We don't have to worry about the inverse kinematics. So in this way, the operators can quickly pick up the scale and immediately do the operation. So again, we would like to show some of the video demonstration after we change the master devices. Here again is the video demonstration, which is a teleoperation. It's actually I myself in the cadaver experiment. We don't have a robot patient, so we are using the cadaver specimen we purchased from a specialized company. And we can see here, this is the new master device we developed, which essentially have isokinematics. We call it so that they have similarity kinematic chain for both the master side and the slave side. And this can significantly enhance the learning experience. So we also invite the surgeons. We can see that later on. So here we also introduce additional mechanism to this parallel continuum manipulator at the slave side, as we can see here. We introduce additional tubular constraint which can move along this direction. And then we can actually modulate the effective length for the continuum or flexible part, which is kind of like elastic beam. So this beam, if we change the free length longer or shorter, we can actually modulate the stiffness. In this way, we can tune the stiffness along the way with our teleoperations, depending on which tissue or what we want to do. For example, if we want to navigate through some of the critical and sensitive tissue, we can utilize low stiffness mode. If we want to have very precise manipulation or high payload manipulation, we can utilize high stiffness. So this is the additional benefit we can have by this parallel continuum with variable stiffness mechanism and also isokinematic mapping. So here we show some of the typical procedures, a few screenshots from entering the oral cavity, pick up the tissue, cut it, and finishing. Eventually, we can see the tissue cut. So this essentially from our cadaver experiment interaction with surgeons, we see that this isomorphic or isokinematic development can enable very straightforward end-to-end master-slave control. So this can avoid complicated kinematic calculation and also avoid the learning, very steep learning curve for the operators. So here you can see a more comprehensive demonstration. So this is the continuum part. We can see three continuum kinematic chain. They are linked up together to close up the chain. That's why we call it parallel continuum mechanism. And we have both the grasper and also the electric cardiac device have this parallel continuum configuration. And we have the vision channel right over here. And then by modulating the concentric tubular constraint, we can change the stiffness. So here is what we can see from the experiments. We can see the force can be changed, can be modulated along the way while we are changing the effective length of the parallel continuum constraint. So here we see this is the master side right over here. This is the patient side right over here. So this is the isokinematics. The kinematic chain for the master side and the slave side are very much similar. So we can see the motion transmission and mapping from the master side to the slave side is very direct and straightforward. It just a little bit scaling factors. We can quickly know how to operate it. And this is to show that by modulating the stiffness, we can actually, in a high stiffness mode, we can have better payload. And this is the surgical setup in the cadaveric experiments. And this is our clinical collaborator. So just a few minutes after a quick trial and error, and the surgeon can learn how to operate the device without taking significant amount of time. And this is an endoscopic view. You can see that the grasper and the cutter can cooperate very well. And so this to show some of our earlier development by introducing the isokinematic configuration between the master side and the slave side, we can make the teleoperation more intuitive. And so along with the way of our system development, so we are experiencing the COVID pandemic as everyone experiencing. So we're talking to the clinicians to see what can we do, since we are working in the field of teleoperation for many years. Essentially, teleoperation can minimize the risk of viral exposure. So no matter what surgical procedure we are, you're doing, the surgeon are doing, because we can effectively separate the patient from the clinical team. So in that case, the upper respiratory digestive system disease, which always have the high risk of virus exposure, if we have teleoperation available, we can effectively minimize the risk. And one of the systems we're trying to develop, this is one of the earlier prototype, we actually do a slight modification to the system we just demonstrated. The actors, the transformer robotic system, and we modify the slave part a little bit. So one of the translation component, we modify it to be the tongue depressor, which is very much needed for the patient who have very difficult tongue exposure, especially for the patient have, for example, the tongue and not be able to fully expose, and the operator is difficult to see or to reach the oral swabbing area. In that case, we need to introduce the tongue depressor. So here we modify the system a little bit. We just utilize one of the arm, and here we can see the overall system setup. Again, we have the master slave isokinematic mapping. They share similar kinematic chain. And here we can also see the prototype demonstration. So this is a workspace demonstration for individual degree of freedom. For example, this one is showing the tongue depressor. What is range of motion we can accomplish. And for the swab stick manipulation, usually we want to have a circular-like motion. So that's what we can see from the videos. And we measure the forces we can generate by the tongue depressor, which is around 8 Newton, which is sufficient for depressing most of the tongues for the patient. And this is to show the visual guided. Essentially, it's the human in the loop. So based on the endoscopic view, directly feedback from the endoscopic vision, and the surgeon can manipulate the oral swab in a master slave isokinematic mapping way. And we have an additional demonstration. As you can see now, we put the phantom, which is not a robot patient, it's just a dummy phantom. You can see the swab stick have a circular motion, rubbing against the backside of the tongue or the softer palate, so that we can take the samples for further lab testing. And here you can see the operation is essentially very intuitive, because they're essentially sharing similar kinematics from the master side to the slave side. Here we can additionally see the flexible beam, which is the parallel continuum. They can tune the stiffness, and also at the same time they can be bended a little bit. So it's not fully rigid nor fully soft. They just can be bended a little bit depending on how much force we apply to the end effector. This is a close-up view. We have the button to control the tongue depressor. And then if we do a sort of circumduction motion or circular motion, we can see the motion mapping from each individual joint to from the master side to the slave side. So that is the additional demonstration to show the benefits of isokinematic mapping. Well, in this ICRA conference, we also published another paper which further pushed the technology to a more specialized, modularized way. So as we can see from the picture, we want to build up a modularized and reconfigurable mini robot, which still have bilateral isokinematic mapping, which can allow us to have fast onset assembly because we have very easy to assemble magnetic connection. So here we can see pretty much the master and slave are sharing almost same kinematic chain. This is the master side, this is the slave side. When you're looking at this picture, we can actually replace them or swap them without changing the kinematics calculation or control algorithm. So this is gonna allow us to have quick assembly and de-assembly in the surgical setup. So here we can see a quick overview of the system components. For one of the key component over here, we have modularized magnetically connected parallel mechanism. We call it 3P4S. We have each kinematic chain, we have one prismatic and 4 spherical joint for each individual chain. And putting up together 3 of them, we can have sort of like delta parallel mechanism motion. And this, on top of this, we can add up additional 2 degrees of freedom so that we can have additional 2-directional bending. So by doing that, we can have more dexterous manipulation. And so we are using cable-driven mechanism so that we can separate the motors from actuators by the cable transmission. When we're looking at the key component here, we can actually utilize magnetic connector to do the fast assemble. At the same time, we utilize the magnetic ball as the ball socket joint, as we can see over here. So here is a video demonstration. You can see some of the performance validation and also the parameters is quite small, and the total outer diameter is around 16 millimeter, 80 millimeter length, the total head over here. So you can see by utilizing the bilateral isokinematic mapping, again, we show that we can quickly build up the system. And this allows us to have fast assembly. So here you can see we de-assemble the components. We quickly remove the current endoscope. That's the first configuration. And then they introduce the scissors from the middle lumen. So we have this magnetic ball here to allow us quickly connect the spherical joint together. And then you can see the scissors are now ready to use. So the overall dimension is small enough so that we can put it inside our cavity. And last year, we changed the end effector to a gripper. So now you can see this isomorphic system can have direct master-slave mapping. We don't even need to modify the control algorithm. We can just put it to the clinical setup, and we do the quick onset assembly, onset interchange in terms of the manipulators. So the next question is, what if we don't have this isometric kinematic chain? So our earlier research experiment, we also introduced image-based virosylvaline so that we can utilize virosylvaline to do some low-level fine-tuning of the kinematics and also the motion control. So what we did is, for the beginning, we can introduce the master-slave, which is again just like the conventional master-slave control, to introduce the teleoperation, so that we can remotely manipulate the concentric tube robot roughly to the surgical area. And then we utilize image-based virosylvaline. In this case, we simulated the scenario that the shaking or some of the dynamic scenario, so the target is moving a little bit. We still want quickly retargeting so that we can keep the marker in the middle of the field of view. So here we have two key teleoperation modes. One is the teleoperation before the virosylvaline. In that case, we can again rely on the human operator to do the fast guidance. And then for fine tuning or fine targeting, so we literally introduce a laser marker. So another operator can shine the laser marker to introduce better image features. We can do the automatic recognition. And then the image-based virosylvaline algorithm can automatically tune the concentric tube robot so that they're pointing to the target. And then we can have this image-based virosylvaline. So in this case, we introduce the manual markers and also image-based virosylvaline to enhance the controllability and also to ease the teleoperation. So this involves very strict supervision and have limited motion understanding. So we can see the difficulty is even more significant if we move on to 13-degree freedom concentric tube robot. So in this case, the master and slave side, this is the master and slave side, they are not sharing similar kinematics. So we need to spend quite a lot of time to learn how to do the inverse kinematics, both from hardware side and also from the control side. So this is one of the 13-degree freedom concentric tube robot we developed. We have 5-degree freedom for each one of the manipulators and 3-degree freedom for the vision channel. So let's take a look at the video demonstration. This is the master side, and this is the endoscopic view to see what's going on in the teleoperation. So essentially, we are picking up a simulated form, and we cut it using the electrocautery device. So here we know that the concentric tube robot typically have coupled stiffness and kinematics. So in this case, we are experiencing a lot of difficulty. So it involves intensive tuning. And then we want to push the technology to one step further with asking a question, can the robot learn like human experts? So when we show a picture like this to the experienced surgeon, they can quickly say, oh, this is a scissor cutting a tissue on the right, and forceps is manipulating the tissue on the left. So that can quickly have some of the human level recognition and communication. And then this is going to be very useful to enhance the training and also enhance the robot control. So this is what we are trying to develop, and we have some preliminary data which is going to be presented in this conference as well. So because of time constraint, I'm going to quickly run over the motion understanding part. So we have been working on the AI real-time instrument segmentation. So we can do the binary segmentation part recognition, and eventually we can recognize the instrument, which is sort of semantic segmentation. And we also introduce different deep learning approach, both for the segmenter part and also the regularization part, so that we can enhance the segmentation. So meanwhile, we also want learn some of the capability like autonomous car, so we can predict the driver or operator attention. So we know that experienced surgeons typically have different focus, have different attention, even though we are looking at the same surgical scene. We are trying to learn from experienced surgeons what their attention is, so that in the future we can transfer their expert knowledge to either the surgical robot, so we can have automatic manipulation, or we can transfer to the training. So this is what we did, utilizing the self-attention learning and also the scan paths to see what is the surgeon attention. They are changing their focus, their gaze for the same surgical scenario. So, and then after this, we want to push the technology one step further. So we already have the automatic segmentation, scan paths, and attention learning. So those segmentation, detection, it's still a little bit far from our human level communication. So we want to further push it so we can generate the scene graph. For example, we can utilize the graph passing network to show that, you know, what is the relationship between the instrument and the tissue. And furthermore, we want produce some human level captions, just like this action triplet. So what instrument is there doing what kind of action, interaction with which target. So this is what we want to do. So we can see some of our earlier development. We can utilize the object node detection, which is a single shot detector neural network, so that we can detect the bounding box for the instrument and the tissue. And we utilize the feature attraction network to learn the high-level features, to embedding the features, and utilize that, we can build up the scene graph so that we can have this scene graph generation. So we can describe the relationship between, for example, the kidney and the faucet. Either they have idle situation or they have different manipulation, could be cutting or suction. So that is the development we have in our earlier research. And this ICRA paper will further push it to the human level communication. So after we have this recognition, we can detect the instrument and tissue and the scene graph. We want to further push it to human language. So in this case, we also want to address one of the challenges, cross-domain adaptation. So we're going to show in the next slide. So eventually, by doing this surgical motion understanding using human language, we can have better description of the surgical scenario. As you can see, this example, a monopolar curved scissor is cutting the tissue. As we can quickly do the automatic scene understanding and explain it using human language. So this is a scenario to show why this is challenging, because we are essentially moving from the kidney procedure, which is captured from the training data shared in the public domain, and now we want to push it to our in-house data collected by our clinical collaborators. And we can see the very significant domain from the histogram and also from this feature distribution. So because time constraint, I'll quickly show a few more slides. in roughly 1 minute. So we also develop a lot of other neurosurgical systems. And here we do the height-mounted system development. We can see the cubicle height-mounted robot. So we're replacing this very bulky, very painful stereo tap-tap frame, which is very commonly utilized in the current neurosurgical procedures. We have different development, a circular one we call the dual polar parallel mechanism. In this ICRA conference, we also share how to do the automatic planning and also automatic remote center motion recommendation. And for surgical, neurosurgical procedure, it's very important to have the sensing, how much force it's interacting with the tissue. So here we have our earlier development. We introduced the FPG sensors. We can have three-dimensional force and torque information in very high resolution. So here, a quick video demonstration. When we are interacting with the tissue, we can see the forces are reflecting what is the level of interaction. This is very commonly utilized the suction or aspiration tubular instrument, which is called aspiration tube over here. So we also have stretchable pressure sensors to detect the tissue instrument interaction. So I have to skip this because of the time issue. We just want to highlight the key thing here that soft sensor technology can also have the potential to push to the robotic patient development because it's stretchable. We can apply it to the soft tissue and they can quickly reflect the normal force interactions. So here a quick summary. So we talk about the hardware level teleoperation from the isokinematic master-slave mapping, the hardware development, and also from the software perspective, we developed the image-based feature learning, human language translation. Hopefully this can enhance the surgical training. And also in the future, we can push the technology to fully automatic surgical procedures after we can incorporate the AI, tactile sensing and many other different sensing modalities. Eventually, we can close the loop. We can have the situation aware and self-responsive, augmented, minimally invasive procedures. So lastly, we'd like to thank the team members. Without them, we wouldn't have this wonderful work. And also some of the papers that I introduced in this talk. Thank you. I think I overran the time a little bit, perhaps.
Thank you very much for the fantastic talk, Professor Chen. We don't have time for questions, unfortunately, and all questions will be delivered in the ideation panels later. Next, I would like to introduce my colleague, Florence, to introduce our next speaker. Thank you.
Good morning, everyone. Hi. Thank you, Professor Ren, for the interesting presentation. Next, it is my great pleasure to introduce Dr. Dan Tirichavam from Newcastle Private Hospital, Australia, as our next speaker. So Dr. Dan is a highly experienced abdominal, upper gastrointestinal and bariatric surgeon. He has great interest in robotic surgery, and we have had an amazing collaboration on magnetic-based robotic system for abdominal surgery some years back in Melbourne. So, hi, Dr. Dan. It's really nice to see you again, and I'll hand the mic over to you.
Thanks, Florence. I hope you can hear me clearly.
Yes,
there.
Can.
Now, with the screen sharing, can you see my slide there, or?
Yeah, we can see your slides.
Okay, fine. Just one thing. Sorry, I'll just see if I can. Yeah, that's probably better there. So, look, thanks very much for the invite. It's evening here. It's morning for you guys there in the UK. And so my talk, I was really quite impressed by Ren's discussion there, and very technical. And I just wanted to talk about how, what is the current status in terms of using robotic surgery, particularly in abdominal surgery, what are its benefits, and how did I introduce that new technology, and also where I see it going, because it's really you guys who kind of develop all of the technology, and then the question is, how do we institute that safely and use it? So I I'm going to talk about where I view the merging of technology and surgery, and where that sort of fits in a historical context, how I introduced new technology, whether that was robotic or endoscopic surgery, what were the challenges of doing that, and what are some tips or tricks? Because obviously, you know, coming on from the end of Ren's talk, there's a lot of things that you want to put into practice, and how do we do that? How do we teach someone that's a novice, whether that novice in robotics is a young trainee, or whether that novice is actually an older surgeon who wants to learn robotics? So that's a little about what I'll talk about today. It's interesting when you go to conferences and meetings and talk to surgeons about technology, you must realize in context that laparoscopic or keyhole surgery really only came in about 1990. So not that long ago. We're only talking 30 years ago. So prior to that, everything was done open. Then it shifted to laparoscopic. And then we've had advances with robotics and sort of more technical endoscopic surgery. So my personal take is that it's inevitable. What you guys are doing, it will definitely come in and we'll use it. But you'll find there is resistance, and that's for lots of different factors. I think at the moment, robotics augments what we do. So towards the end of Ren's talk there, he talked about sort of autonomous procedures and so on. And I think we're still quite a distance from that. But one of the interesting parts that he talked about was using the expert surgeon and learning their motions, as he said. I think it was ScanPath he was talking about, to learn those motions and then kind of use that to train people. I've made the fourth point. It has a long way to go. So for lots of reasons, it takes a long time between development of the robotic technology, instituting it, getting it cost effective, and getting it into patients. But I think there's a lot of benefits for minimizing fatigue, both mental and physical, reducing tremor reduction. So a lot of what the robot does, I mean, puts an interface between the surgeon and the patient. And as I sometimes joke, it'll allow me, I'm in my sort of mid to late 40s, but it'll allow me to keep operating maybe till I'm 80 rather than, you know, retiring at 65. So it gives you visual aids. So I just want to talk about the concept of introducing new techniques and technology, and I did that with both of these. So one's a robotic procedure, the robotic gastrectomy, and the second one is a POEM, which is not a robotic procedure, but it's an endoscopic procedure. And the method that I used to introduce both of those were the same. So that is that it's something, it's new, it's different, it's highly technical. People aren't used to doing it. How do you do it? So POEM is this, where essentially it was really pioneered by a Japanese surgeon, but essentially we cut into the esophagus with a flexible endoscope and then dissect down in the wall of the esophagus, cut all of the muscle and come back out. So a truly notes procedure. And this is the standard of care of how I now do achalasia surgery. But if I look back when I was training, I didn't train in this at all. In fact, I trained in this after I was a consultant surgeon. So what did I learn from instituting that? And what did I learn from instituting sort of robotic gastrectomy? So I thought of the steps like this, so that you could break it down into being aware of the new technology, but the surgeon needs to be educated, the team needs to be educated. You really need to practice with a dry run with all of the equipment and staff, that we allocated a specific time, so time with no pressure on other things, which I'll come to in a moment, that you have an expert team and that you know how to manage it. So a couple of the things that I noticed in the last talk was that there were, for example, parts of a procedure that were being done with the robot. And one, when you're bringing that in, these are all the steps that we need to go through. So when I talk about education of the surgeon, for example, what Ren was talking about is that there needs to be a collaboration between the producer of the technology, and then whoever commercializes or brings it in, and the end user. So, for example, if you talk about the Da Vinci robot, most people who use that, because that's the most commonly used platform in the world, that Da Vinci themselves run courses, and they are for the surgeons to then know how the machine works, what it's capable of or not capable of. And so they run both courses which are sort of dry lab courses, cadaveric lab courses, and then they take you to high volume centers. There are obviously a whole lot of other things. There's online resources, there's videos. The robot itself has a simulator, and that's very useful, so that we learnt on the simulator how to make all of the basic motions. Because in fact, one of the things, again, Ren talked about was that memory of, where does this instrument sit, what task is done by that instrument. And so when you're learning new technologies, you have to learn a whole lot of different motions. So the way, for example, if I was to do a keyhole or laparoscopic gastrectomy versus robotic, the ports may be similarly placed, but the motions that you make with your hand are actually quite different. So then observership. And then part of that is also then that you obtain a proctor, and then that proctor comes along and assists you during your training. One of the key steps was you absolutely must summarize every single step of the operation and the way that the procedure works, and obviously memorizing the steps. The second part is that it is very much a team effort. So if I think about it, and you're introducing some new robotic technique, as I say, there's got to be an interface between, for example, the way Da Vinci does it is there's a representative of Da Vinci who comes to help the nursing staff and the surgical staff sort of institute the procedure. You need to take your team along, so you can't just institute a new technique and not bring everybody along for training. As I say, set expectations and in fact use a usual team. So we would use our normal scrub team. So I'll give you an example. Today I was operating here upstairs, and I can finish my procedure, I can see the next patient, and I can walk away, and I come down to my office where I'm sitting now, and then somebody will call me and say we're ready to go, and I'll walk back upstairs. The team has exactly everything in the right position, the right equipment, bang, 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 I can start the operation and go. So that's very important in this new technology introduction, that you have those kind of teams. The next step I'd like to talk about is a dry run. So with new technology, and particularly robotics, and this is not a picture of a robotic theatre, this is a laparoscopic theatre that you can see. You do everything, and you run through every step of that operation, but without a patient. So you would get your normal anaesthetist, scrub nurse, theatre tech, whatever, and work out all your positioning, all the scenarios, all of the roles, all of the equipment and where they are. And you've got to have a lot of redundancy. So that means you've got multiple pieces to that robot that you're going to use from an interchangeability point of view. And that way, when you actually get to the first procedure, you're not worrying. Your brain does not have cognitive overload with thinking about where's that other piece, this little bit of equipment's not working, no one seems to know what it is. That just builds up the stress in things. So redundancy is very important. On the day of the actual procedure, so both of these, both POEM and also the, say, robotic gastrectomy, you would get a proctor in. And now, interestingly, if you were really doing some of the first ones, well, you wouldn't have a proctor. So you'd instead have an expert surgeon, and then they would attend. As I've mentioned, there must be no time pressure, no equipment pressure, no staffing pressure, an experienced assistant. And this last point is extremely important, that we would have the conversion tools to change from that robotic procedure to a laparoscopic or open procedure. that's sort of highly critical. The other part I think is very important is post-procedure, that there's a debrief, you understand all the steps, you go through that with the team, you video the whole thing. So again, when I started doing it, I would video both the actual procedure, but a separate video looking from the outside at where the equipment was positioned and so on. The other clinical part is that we log all of the cases, we audit them, we look at complication rates, and you'd continue to have your proctor in place until you were happy that you were able to comfortably do things. So the second part of my talk, and I'm mindful of the time, so I'll try to stick to time here, is that when we are teaching somebody, the robotics comes in. So you can see in this picture here that there are two consoles. There's the robot over here. This is obviously a patient, but you could do this with a cadaver or some other model, and both the surgeons can assist each other, right? This is quite amazing in terms of how you could teach a novice. The current issue, and this is worldwide, is that students need to practice, but the appetite for practice in a clinical setting is going down, right? So as you can imagine, as a patient, you probably think, well, look, you know, I'd rather the expert surgeon do the operation than the one practicing. But we need to teach them, and we need to teach them particularly complex operations. So where robotics can help you is that you've got to teach them anatomy, dexterity, accuracy, tissue tension, dealing with complications. And this is a lot of cognitive load on the trainee. So if you can somehow break that down or control the pathway through which they learn, that can help. What we're also seeing, and this is kind of worldwide, is less exposure to patient cases. And as I mentioned, less tolerance for training. So if I think about the steps, you think about simulated practice when you're training somebody. There's direct supervision, there's indirect supervision, and there's independent work. And they're the stages that we sort of go through. Where the robot can particularly help, and in fact, again, just going back to Ren's talk, is that when you're doing that simulated practice, the robot may actually say to you, listen, your right hand is too far out here or there. And so therefore, you know, they can draw you those little rectangles he had to suggest that your instrument should sit here or you should grasp like that. And I think that takes a lot of stress out of the training. And then, you know, they can then subsequently sort of go through all of those steps. An example is there's a procedure called helosmotomy. Essentially, it's like that poem procedure that I told you, but it's done keyhole or laparoscopically, and you're effectively splitting all the muscle on the esophagus, particularly the distal part or the lower part. So that means of the muscular tube that you normally eat, you're cutting all the layers except down to a few millimeters of the mucosa and submucosa. And I can tell you personally that over the years, I found that very difficult to teach somebody, because it's an operation that has very little room for error. And when there is error, that can be very difficult, or the morbidity and mortality rates is much higher. Where the robot can help you is that you can actually sit and use a cadaveric model or one of these plastic models, and then set it all up to try and do the procedure. And so you know exactly where are the instruments placed, how do I do that technique, what happens if I have a problem, etc. And then that takes the stress out of what is a procedure done in an, it's an uncommon procedure done in, a rare condition. So I think that again is where I see robotics sort of taking off. We talk a lot about robotics, and I'm sorry I was caught up and I missed the first bit of Ren's talk, but some of the real negatives now I can tell you that it's slow. Okay, so we theatre time is expensive, so why are there not large volumes of, why hasn't everything gone from laparoscopic to robotic? It's slow, it's expensive, there's delay in movement and changing instruments over, and lack of haptic feedback is another reason. So and this is where you guys really come in, when we can make it faster, when we can get more haptic feedback, they're the things that we really need. So I think in terms of future directions around clinical use of the robot, as I mentioned, it really must, to get into clinical practice, be more dexterous and faster, and more ability to mimic the speed of a human's hand, and that we're really not at that point yet. The eye tracking is very important. There is obviously a lot of work being done on that. Robotic flexible endoscopy, which I understand there's a talk later on. The haptic feedback, or the sensing or simulated sensing, is extremely important. And obviously there's the cost factor. The current systems are very, very expensive. Again, just I cut some of Ren's stuff and put it in here at the last minute, but the scan path that he talked about, I was most impressed at, and the surgical motion understanding, and obviously overlaying of image guidance. And one of the things I think about, where I think you guys can take us much further, is when I drive my car. My children were asking me the other day, Dad, you know how to get from point A to point B, so why do you use the navigation system, right? You've done it so many times. And I said, well, that's an interesting point. I said, I can do it, but what this allows me to do is I just set the thing on, and that part of my brain is turned off, so the rest of my brain can talk to you, the children, or listen to some music or do something else. And that's where I think the robotics will come in, instead of the mental fatigue of constantly looking at all these different things, and the physical fatigue. That guidance in those little boxes, and if you stray out, you get a little warning, or you get a guidance. That's going to allow us to do much more and utilize our brain. So look, I'll end that there, and not quite as technical as Ren's talk, but I thought that might give you some idea of where you might want to go in terms of a lot of your research. Thank you.
Thank you so much, Dr. Dan, for the really exciting and insightful talk. All right, so as we have limited time for question and answer this round, we will gather the questions to be addressed in the ideation panel discussion after the talks. And yeah, we'll have a 10 minutes break, and Ryman will call upon our next speaker after. So thank you again, and we'll see you back here in 10 minutes.
Yeah, Raymond, are you there, right? Yeah, muted. Yeah.
Yep.
Yeah.
Perfect. Let me see.
Yeah. Professor Bin, are you there? Yeah, he's here.
Professor Ben, yeah.
Raymond, I think you can.
All right. Hello, everyone. Thank you very much for joining us in this ICRA 2021 workshop. Will be a lot of interesting talks actually coming up, and we'll introduce starting with Professor Bin Feng from Tsinghua University, and he works on tactile visual fusion for medical training and manipulation. So Professor Ben, the floor is all yours. Thank you.
Thank you. Thank you so much for inviting me this talk, and it's my honor to introduce my work. And I'm from Tsinghua University, and I'm focused on tactile technology and use tactile visual technology as a fusion for medical training. And my report can be divided in these 5 parts. And first is introduce the background of my research. And in traditional Chinese medicine, the traditional diagnostic method consists of look, smell, ask, and feel plus. Looking means to observe a patient through vision. Hearing means to judge by sight, and asking means to ask about the patient's condition. Feeling the plus by our fingertip, because the fingertips have the strongest tactile perceptions. And among the feeling and knowing the plus is the most difficult technology. It also shows the importance of tactile. And in modern medicine, tactile is also very important. Although doctors use robots to perform all kinds of operations, there are high requirements for doctors' tactile perception. And at the same time, in order to increase the safety of operation, tactile sensors will be installed on the surgeon instrument to increase the perception ability of the operation. For example, hyperparacytic overall tactile sensor is developed in robot assistant mirror investor surgeon, and also we can see that the modularized optical tactile sensor was developed for mirror investor surgeon. And in recent years, I have also developed some tactile sensors, mainly include capacitive tactile sensor, and the piero-resistive tactile sensor, and visual-based tactile sensor, and also, and in this ICRA year, the work is also related to our vision-based tactile sensor. And then the first 2 kinds of flexible electronic sensors, and next I will mainly introduce the electronic tactile sensors. We have developed the 4 generations of captive tactile sensors. The sensor used high elastic micropin that is inspired by human fingertips like cell. The tip of pin ensures high sensitive performance of the sensor under initial stress condition. And meanwhile, the larger diamond root of pin ensure the sensor has greater pressure bearing capacity. And the performance of different elastic insertion layers was modeled and simulated. Due to the high elastic of material and the structural design of the microspin area, when the force is unloaded, the deformation is quickly recovered, and the elastic surface can be spotted. So we use our lead sensor and they are equipped with the robotic fingertip, and we can see that it can highly similar forces and capture objects property in manipulation of our robotic hand. And we also use the sensor to measure the Laplace of rest as shown in figures, and our results were consistent with the normal pulse range, about a minute, about 20 to 100 times. And in order to reduce the cost of our tactile sensor area, and the piezoresistive tactile sensor is also developed. The structure of tactile tactile sensor is consisted of 5 parts, and there are 25 season points. So we can see the details of index in this table. And we integrated our tactile sensor into the prosthetic hand, and we can after the prosthetic hand integrates with the tactile sensor, and it can stable grasp something and can help FTs to manipulation and grasp stable things. And we also developed the larger area tactile sensor for knee arthroplasty. And the doctors need to detect the pressure on the moving surface of the knee joint to determine whether the thickness of femoral prosthetic is appropriate. Therefore, we developed a large area tactile sensor, and it can be realized the real-time detection of intraoperative pressure. And here you can use the in the porker's knee to light this function. And based on the previous tactile sensor, we also developed the tactile data growth, and the tactile data growth is developed for understanding the tactile behavior of sampling and fine manipulation of micro components. and it's also a very meaningful application signal. And it also and this growth is also can be used in medical training. We know in the process of surgical puncture, it's difficult for new hand to locate the area, the place of punch, and therefore we proposed a method for visual and tactile fusion to assist the localization. We combine the horns to realize the puncture localization, and then use our wearable tactile fingertip to further convert the corrected punch precision. And combined with the human surgical model, the simulation mode is designed, and the virtual real fusion modeling is carried out in Unity 3D software. And meanwhile, the punch point is augmented reality through the modern matching and relies the position assistant guidance. And according to requirements of the punching training, the fingertip equipped with tactile sensors to extract the future classifications to judge the parts touched by the fingertip, and we can real-time voice playback parameters to effectively identify the punch parts. And by extracting the fusion of visual imaging information and the tactile features respectively, and a tactile and fusion punch site localization based on machine learning algorithm is designed, and it can be to ensure the accuracy and the reliability of punch on operation site. And, yeah, and another aspect that for new hand, when the punch can be gets through the skin, it's also difficult to accept it. So we placed on the tail of noodle, and combine the tactile sensor with the magnetic position sensor to realize the touch perception and achieve the accelerative function of pattern perception. And the tactile sensor is placed at the tail of noodle, and the positive pressure in the noodle punch is measured. We can find the pressure gradually increase in the process of puncture, and the value at the moment of puncture decreased significantly caused by a season of breakthrough. And meanwhile, we also use a magnetic position sensor to determine the displacement informations, and finally the online perception of function is realized, and we can and based on this technology, we built the expander platform, and including HoloLens and some other components. And here. yeah, is a Chinese video, and the guided disposable platform for self-help, and the experiment of platform was built, and the response time of the algorithm was very second, and through more than tons of experiments, and the precision and localization accuracy was about more than 90.5%. And yeah, we use visual and their perception to help to punch. Yeah, and and also we developed we also developed the orthophysical swabber robot with the tactile and vision fusion, and the RGBD RGB camera is used to detect the sample localization of the swabber tip, and the tactile sensor is also used to assure the safety of sample, and then the robot can automatically detect the sample localization with a real-time machine learning algorithm, and a dedicated control stages based on the tactile information is then applied to safely collect local samples from our slot. Yeah, we can show this video. So the fusion of tactile and the vision promises the safety of collecting samples by our robot. Yeah, and it can keep safe and the right pace to collect. Yeah, and the conclusion of my including 3 points. First, the tactile is very important in medical training and the surgeon operation, and I think in future using tactile to represent the operation skills of experienced doctors will be an important direction, and it's also an interesting direction in future, I think. And through the fusion of vision and the tactile, it can effectively assist the doctors in treatment or further improve the autonomous operation capacity of medical laboratories. And recently, I published the book in spring, and the book is introduced the robots imitation learning based on human demonstration with developed the wearable device, and I hope welcome everyone to download and communicate. And I also show the email, and thank you. Thank you.
Thank you very much. Thank you very much for the interesting talk and presentation of all these tactile sensors. Just a reminder, if there is any question, please ask them in the chat, and then will be further discussion in the ideation session. I'll introduce the next clinical speaker, Dr. Masayo Yamazaki from Jitchi Medical University. And she works on pediatrics training in Japan for students, residents, and patients' families. Dr. Masayo, please, the floor is yours.
Maybe we can, yeah.
Can you see my slides?
Yes.
Yes.
Yeah. Okay, thank you.
Okay.
I'm talking about pediatric training in Japan. Let me briefly introduce myself. I am a pediatrician from Jiji Medical University, Jiji Children's Medical Center, Tochigi. This is an overview. First, I'm going to present the medical education system in Japan. Then I'll share with you pediatric training for medical staff and also for the patient's family. Finally, I will talk about future techniques I hope to have in the future. First, let me give you a brief explanation about the medical education system in Japan. Students start their medical education soon after graduating from high school. This is undergraduate medical education. It is 6 years long, consisting of 4 years of preclinical education and then 2 years of clinical education. Clinical education allows students to learn at the hospital, see patients, and learn practical skills, but historically it doesn't include invasive procedures. After graduating and obtaining a national license for physicians, they begin 2 years of postgraduate clinical training to acquire the skills to perform standard procedures, including invasive procedures. They also take advanced postgraduate clinical training for medical specialists, including pediatricians. This summarizes the conditions under which students, residents, and fellows are allowed to practice. These indicate all procedures are permitted, and this indicate only non-invasive procedures are permitted, and this means no permission. As you can easily find out, medical simulation training is certainly allowed for all medical staff, but it is only available at limited numbers of institutes, especially in the case of pediatric training. Now, let's look at pediatric training for students, residents, and fellows. To start with, let me ask you one question. What do you think are the 3 areas where children differ from adults when you perform medical practice, especially invasive procedures? My answer is 1, their body size, 2, their thick subcutaneous fat, 3, they're rejecting the procedure. Body size, children are smaller than adults. No one will disagree on this point, but it often makes it difficult to take an IV line or conduct lumbar puncture procedures. Thick subcutaneous fat, this makes it hard to locate where veins run when taking a blood sample or placing an IV line. Reject the procedure. This is actually a very important point that often makes it difficult for young doctors to achieve successful procedures. They kick and punch us, seemingly with 200 or 300% of their power. These are two common procedures in which young doctors train first: peripheral venous catheter placement and lumbar puncture. First, we are looking at the peripheral venous catheter placement, taking IV lines. An IV line is usually placed on a hand or a foot. Look at this infant in the picture with typical thick subcutaneous fat. It is not easy for us to locate veins. And as you can easily imagine, children's veins are usually thinner than those of adults because of the small body size. Now, how do we locate the veins? We use a transilluminator. I personally use the one shown in the picture on the right. This is a must-have for a pediatrician. When you turn on the switch, the light comes up and you can see the veins like a shadow through the light. This allows you to locate the vein underneath the subcutaneous fat, but it's not perfect. It is important to check all the hands and feet for the veins most suitable for the procedure. Now, do you think you can easily take an IV line once you find the appropriate vein? The answer is no. What else do we need other than a transilluminator? We need to appropriately immobilize the child. This is a very important point that prevents young doctors from successfully performing procedures. The picture shows a child undergoing a blood test. How many adults can you find in the picture? There are 3, but we sometimes need even more adults according to the child's temperament. Remember, children always reject the procedure and with 200 or 300% of their powers. They kick and punch. We must always be ready for them. Keeping them immobilized during the procedures is important for the safety of both the child and medical staff. Next, let's look at the lumbar puncture. Lumbar puncture can be done in a lying position or sitting position. Here we prefer lying position. The procedure itself is the same as for adults, but it is sometimes difficult to locate each spinal process because the interval of each process is narrow. Again, you must make sure the child is appropriately immobilized before you start procedures. We sedate the patient or use local anesthesia as necessary. In the picture, we only have one adult holding the child, but we often have 2 or 3 adults. Next, let's look at the training for the patient's family. As more home care patients require special care, such as ventilators and nasogastric tubes, we have more opportunities to teach their families how to replace tracheostomy tubes and nasogastric tubes. The family must be trained in basic life support or BLS. They also must be able to place a tracheal tube or a nasogastric tube as necessary. We use a training mannequin for their training of BLS. Here we have baby Anne. When they train in the replacement of a tracheal tube or nasogastric tube, We first let them see medical staff carrying out the procedure on their child several times. Then we let them try on a training mannequin, baby arm. It is totally imaginary rehearsal because you cannot insert a tracheal tube or gastric tube into a mannequin. They usually repeat the training with a mannequin for days or weeks. And finally, they try it on their child. Can you imagine how they are feeling during the training? We often see them feeling stressed, anxious, or afraid during the training, especially when they try it on their child for the first time. What do you think pediatric patients who need special care look like? Maybe like this. But sometimes they are like these too. They can move around, laugh, and communicate with you. So again, you must keep in mind that they may reject the procedure. Future techniques. This might be a bit different from your research area, but I believe that good techniques improve staff skills while the child's safety is guaranteed. In pediatric work, new techniques are requested that are not invasive, that require no sedation, and that gives us results quickly. Let me show you two examples. My first example is an EEG. It is non-invasive for sure, but young children require sedation because it takes 30 or 60 minutes to place all the electrodes, the small things, on their heads. I hope the electrodes will be placed easily and quickly and give us results accurate. Second, when a child with diabetes insipidus, DI, which causes polyuria, undergoes surgery, we must monitor blood natrium concentration for days after surgery. We need to take blood samples many times a day. It's invasive, and we must immobilize the child if needed, and it takes up to 1 hour to get the result. Will continuous natrium monitoring system be available when we already have a continuous blood glucose monitoring system? So the summary. Simulation is applicable for all medical staff, but it is available only at limited numbers of institutes. Simulation is also helpful in preparing the child's family for home care. We must immobilize or sedate children whenever we carry out invasive procedures. In the future, I hope new techniques will be developed that will change these situations to keep everyone safe and happy. That's all. Thank you.
Thank you very much, Dr. Masayo. Was really interesting, and you gave us a big question: where is the invasive method is the best option, or should we find an alternative before we build all these tools? So thank you very much. My colleague Liang will introduce the next speakers. Liang.
Thank you. I will introduce you with Professor Mustafa Sufi Erden from Heriot-Watt University. He's leading research in the area of human-robot interaction, medical robot, assistive robot, and skill assistance. We are delighted to have him in the workshop to give us a talk on the topic of robot surgery trainer and experimental and development platform. So the floor is yours, Professor Sufi Erden.
Hi, everyone. Can you see my slides?
Yes, we can see your slide. Yeah.
Okay, great. Thank you very much. So, hi everyone. My name is Mustafa Supi Erden. I'm an associate professor at Heriot-Watt University in Edinburgh. So today, I will introduce you the robotic surgery trainer, an experimental platform, a development platform that we built in our laboratory. For us, why we built such a system? Because we needed something to be able to make research related to robotic surgery. We looked at how people are training for robotic surgery, and it's like this. So surgeons, of course, they are using the simulators, first for the Da Vinci system, specifically, but the platform, they get their first physical robotic manipulation experience is actually with the actual surgery systems, with the actual systems they will be using in their operations. So what is the problem with this? Perhaps the best platform, because you have one-to-one experience of what you will encounter in your surgeries later for your training. However, the reality is that these systems are very expensive, and buying one for training is very costly. I mean, hospitals, large hospitals can afford one or two of those systems, and asking them to buy another for training is really expensive. And once, sometimes the same systems are used both in operation and for training in hospital, for training is very low. And finally, if it is any, I don't know, usually there is no way of using those systems that are used in training for research purposes. So as a lab, I cannot imagine going to a hospital and making a research with the Da Vinci system there. So overall, there's a kind of lack of some low cost and simpler systems which what surgeons have with their robotic surgery. So to address this, we developed this system. So what you see in the video now, I hope you can see the video, is the system we developed. So this is two UR3 robots, a laparoscopy training box, a standard laparoscopy training box, standard forceps attached to the end effectors of the robots. The robots can manipulate those, and some servo motors to activate the forceps and their orientation. And then manual tools. Here I'm showing the touch haptic device, but it doesn't need to be. These hand controls can be anything. Actually, we applied video game joysticks. We applied keyboard control, so they can be replaced. They can be replaced also with the actual hand tools that are used in robotic systems. The actual hand tools that are used in Da Vinci system can be brought here and used. So this is a system that allows us to perform some research on robotic surgery related things. But it is more than that. Its abilities for training as well. So it can be used for training for the surgeons. But first of all, let me show you a list of the main components in this system, just to highlight that this is a low-cost system that many of the laboratories, component here is perhaps the UR3 robots, which are among the most affordable robotic platforms, I would say. And many of the robotics labs have these robots nowadays. Then there are the force torque sensors. I will talk about this. We use those force torque sensors to provide some haptic feedback to the user. So laparoscopy training bags, forceps, servo motors, all very low cost components for a laboratory. Processors, Arduino processors, so touch haptic devices, 2 cameras. Again, there's nothing expensive here for a laboratory. 3D gaming headsets, a laptop, and the software that we developed to control this system. And this is the overall system. So what are we doing with this system, or what we aim at doing? I will show you a few examples now. So the first thing we wanted to do was a provision of remote access to such physical system. So what you see in this video is on the left-hand side, one of our researchers is controlling the robot remotely through internet connection. Actually, he did this from his house in Edinburgh. So within Edinburgh, our laboratory is also in Edinburgh. Within the city, it worked very well. So why are we doing this? I mean, what is the sense of provision of an internet access to control such a system? The idea came from our surgeon collaborators working on a training center. They were mentioning this limited accessibility of a physical system that can give the surgeons the feeling of what is going on with the robot. And they suggested whether it would be possible to have some kind of internet connection and remote control. And in response to that, we developed this. And now our system is possible to be controlled remotely. And the person who is controlling the robot gets the video stream that from inside the laparoscopy box, so they can see what they are doing with the robot, and then they can control with the keyboard. So this another thing that we implemented with our system was 3D vision. This is because, I mean, the new versions of DaVinci system provides 3D vision. So surgeons have 3D vision of the system. So we wanted to implement this, and actually it was surprisingly quite simple to implement the 3D vision. It was just a matter of placing 2 cameras to get 2 images, of course. Here you see the videos on the right and left side cameras, and then to stream these right and left side images to the 3D vision headset, to the right eye and to the left eye, and then you get the 3D vision. And we have now our system which is compatible with the current DaVinci system, for example, considering the 3D vision facility. And another thing that we have been working on with our system is the haptic provision. As the previous speakers have highlighted, haptic provision, force feedback, is very important. So, and this is lacking with the current robotic surgery systems. So, but we believe that this will come. So robotic surgery systems will, in near future, I would say, will be equipped with haptic systems. So the main challenge with provision of haptics with robotic surgeons is the sensing of the forces. So the tooltips are very small, and placement of sensors there and cabling is the main challenge. So we are working on this problem as well. I will not talk about that, but we are envisaging developing some miniaturized sensors with minimal, with the current training system. We don't need that. We can use some force sensors at the end effector of the robot. This is not very precise. This is not the precision, the level of precision that we would like to have ideally. However, it is very useful. It still provides a lot of haptic information to the user, and it provides a very good platform to study, to research the promises of this haptic provision. And we are doing that currently with our system. And finally, what I want to mention is movement identification for training purposes. The video you see here is actually from a laparoscopy exercise. A surgeon is doing this exercise for us with our laparoscopy setup. It is not robotic surgery. It is not with our robotic surgery training setup. It is conventional laparoscopy. So with these videos, we collected various videos from professional surgeons and novice people as well. We can track, actually in real time, here the instruments are tracked. And later we made use of these extracted trajectories to identify what the surgeon is doing. So we classified the movements of a typical surgery like settling the needle, crossing the skin, pulling the needle, not tying, and our machine learning algorithm could learn to identify and to tell us what the surgeon is doing at any moment. So what is the implication of this? Actually, for robotic surgery, it is easier to track the instruments because the robots are doing the movement, and you in real time immediately have the trajectories of the tools. The robot encoders provide this. So once you have this, you can run artificial intelligence, deep learning algorithms we have been using. We have been using also other techniques to identify what the surgeon is doing and whether the surgeon is doing in a good way or in a novice way. So we can identify whether it is professional or novice type of movement, and we can provide feedback. So such a machine intelligence algorithm equipped with our robotic surgery setup, I believe it would provide a very nice, very useful training platform. So this is what I wanted to share with you. Before closing, I would like to give credits to my colleagues and thank to them. So Stewart, Robin, Daniel, Carlos, and Andreas were people who developed this robotic training system. Amongst these were the main contributors. Thank you very much. And I would like to thank you for your attention. Thank you very much. I would also like to thank the organizers for inviting me to this workshop. Thank you.
Thank you, Professor Sophie Erdin, for the interesting talk. Next, I will pass to my colleague to introduce another speaker.
Yeah, thanks, Leah. For the next talk, I would like to welcome Professor Kazuo Kikuchi from Kyushu University. He's currently a professor with the Department of Mechanical Engineering, Faculty of Engineering, Kyushu University, Japan. His research interests include biorobotics, human assist robots, rehabilitation robots, and applications of robotics in medicine. He's a fellow of the Japan Society of Mechanical Engineers and Society of Instrument and Control System Engineers. And also he is a senior member of ICRA. Today, he will going to talk about modeling in robot assistance systems for medical training. Over to you, Professor Kikuchi.
Okay, thank you very much for the kind introduction. So can you see the slide?
Yeah,
okay.
we can see. Yeah.
Okay. So I'm Kazuo Kiguchi from Kyushu University, Japan. So the topic is the modeling. Okay, so the title is modeling in robot-assisted systems for medical training. So in order to provide practical and effective robot-assisted systems for medical training, such as surgery training and diagnosis training, appropriate models, such as medical doctor models and patient models would be important. So in the case of models of medical doctors, skill models of skilled medical doctors will be important. And that skill model will be useful for the robotic surgery also, and also the surgery planning. And that model is also used for the skill evaluation of trainees. So to evaluate the skill sensing is also important. Okay, and also in the case of models of patients, organ models for surgery training will be important, and that will be important for the robotic surgery also. And the symptom and reaction models of the patient are also important for diagnosis. Furthermore, palpation models of the patient will be important also for diagnosis. So for the models of medical doctors, we must evaluate the skill, we must provide the skill models of skilled medical doctors. That means the movement and force, and timing, and procedure of the surgery skill will be important. So to evaluate the trainee's skill, we also must measure and evaluate the movement, and force, and timing, and procedure of the skill. So we need a skill sensing device or skill sensing sensors. On the other hand, we need models of patients also. So for the surgery training, organ models will be important. So for the organ models, physical models, that means mechanical properties will be important, and also the visual models that include tumor, swelling, color, etc. Those kind of visual models are also important for the organ models. And symptom models of the patient are very important for diagnosis. So to provide the symptom models, we must provide the visual models, that is color, rash, tumor, swelling, etc. So those kind of visual models must be prepared. And also we need the physical models. So in this case, mechanical properties are also important. And the movement of the symptom models is necessary. And so conversion and muscle stiffness, cough, etc. Will be necessary for the symptom models. And also reaction models of the patient for diagnosis is important. So active models, active movement, that means reflex motion and pain expression will be very important for the reaction models. And also we need a passive movement, such as joint resistance. And that facial expression are also important for the reaction models to figure out the condition of the patient. And furthermore, the palpation models of the patient is important. So that means the physical models, including the mechanical properties, will be important for the diagnosis. So the models of skilled surgeons model and force generated during the surgery are important to evaluate the skill level of the surgery trainees. And that appropriate patient models in which the properties of certain organs are properly duplicated for surgery should be prepared for the surgery training. The appropriate patient models in which the symptom of certain disease and the reaction result from those disease, and also the reactions result from external stimulation are properly duplicated. Should be prepared for the diagnosis training, such as inspection and palpation training. So in the case of organ models, several good models are already proposed, and those models are used for the automatic puncture manipulator, or to evaluate the force. So force model is proposed for the organ models, and sometimes those models are used for the virtual reality simulator for surgical training. And in addition to the force, reaction force, a deformation model is also important. So for the reaction force from the organ model, several models are already proposed. So there are FA model or spring damper model, and also the stiffness force model, friction force model, and cutting force model are prepared. So we to prepare those realistic organ models, we must investigate their mechanical properties. So in order to investigate mechanical properties, many experiments are already performed, and sometimes they're performed in vitro, and sometimes they are performed in vivo. So actually, in vivo model is preferred for the training. However, property measurement is relatively difficult compared with the in vitro measurement. And also, in the case of in vitro measurement, sometimes it's difficult to measure frequently due to cost and ethical problems. So in vitro measurement are relatively easy to measure. However, the property may be different from in vivo measurement. So we investigated the property change between the in vivo measurement and the in vitro measurement. So property is changed over time. And this experiment is performed with the same individual animal. And for that in vivo measurement, needle insertion experiment is performed. So in this case, the puncture depth is 20 millimeter, and we have several puncture rate, and puncture is performed 3 times for each speed, and sampling frequency was 200 Hertz. Okay, and the same experiment is performed in vitro, and we compare the properties. Okay, so we got this kind of result, and this red line in the bottom is a result of the in vivo measurement, and the rest of the lines are result of the in vitro measurement. So we can see there's a difference between them. Okay, so if we model with measures the coefficient for this model, fx. This is a Kelvin-Boltzmann model. So in this case, especially the coefficient beta is different between the in vivo and in vitro model. So for that, to realize the realistic models for the training, we must be careful about this. And also the important thing is property of organs are changed with illness. So if there is a cancer, then the properties of that part is much different. So to prepare the training model, we must prepare those kind of illness model. But those properties are difficult to measure. So actually, as a matter of fact, preparing those properties of illness are sometimes very important, very difficult. And also, the model for the skill and for the skill evaluation in surgery, we perform the laparoscopic surgery experiment. So, so in the laparoscopic surgery simulator, objective evaluation of the forceps manipulation technique is necessary to provide the effective training. And to perform the objective evaluation, right, it's important to clarify the difference between the experienced surgeon and the beginner in forceps manipulation. Okay, so to clarify the difference between the experienced surgeon and the beginner, the suturing motion was measured and analyzed. So this is an experimental setup. This is a box model. So box model is frequently used for the training of laparoscopic surgery. Okay, so we perform suturing motion with this box model with our experienced surgeon and beginners. And this is a sensor forceps we have used in the experiment. So using this sensor, the motion of the forceps and also the force applied to the tip of the forceps and the force applied to the handles of the forceps can be measured. And there's we performed the fast motion. Fast motion is the motion that the subject threads a piece of needle through a swine liver. Okay, so in this case, we can find out the difference between the surgeon and the beginners. And we just compare the resultant force of forceps and the needles, and the direction of the force is also very important. So in the case of surgeon, experienced surgeon, the difference is small. However, in the case of beginners, the difference is large. Okay, so that means a beginner couldn't transmit the force to the needle effectively. And it is important that the operator generates the force in the direction of the needle for the surgery. And for the second motion, subject tied a wound on the swine liver with a piece of string. So in that case, we also find the difference between surgeon and beginners. And in the case of surgeon, the shape of the force applied to the tip and the force in the handle is very similar. But in the case of the beginners, it's different. So in the case of the beginners group, the force couldn't be transmitted to the needle properly. Okay, and the force generated by the beginners was transmitted to the other place, such as trocar, instead of the tip of the forceps. Okay, so this is another difference. So I just explained the result. So this result concludes that beginner cannot operate forceps well in the non-dominant hand. Okay, so these are the difference we found.
Sekiguchi, we are running behind schedule.
Okay. Yeah. Okay, so I just skip this one. So for that modeling, deep learning will be important for that modeling, including the palpations. Okay, so to make that effective models, we need that both medical doctor's model and patient model. Okay, so this is a summary, and that's it. And sorry for that.
Yeah, so
okay.
Thank you very much, Professor Keguchi, for that interesting talk. Since we are running out of time, I will invite Trish to handle the session. Trish.
Hello. So next is Ariana. Right.
Yes,
so,
I am here.
Yeah, I have the honor of introducing Professor Ariana Menchasi. As I first met Ariana, I think back in 2014, something like that, when we were working together in this European Union funded STIFLA project. And then since then, it has been a privilege to be working with Ariana in a number of other activities. Professor Ariana Menchasi obtained the PhD in bioengineering in 1999 from Scuola Superiore Sant'Anna, Pisa, Italy. At present, she is a full professor of biomedical robotics at SSSA and team leader of the surgical robotics and allied technologies area at the Biorobotics Institute. She is an associate editor for Soft Robotics, and she serves as the associate editor for the IEEE Transaction Robotics from January 2021. She's a co-chair of the IEEE Technical Committee on Surgical Robotics. She received the Weltec Award from Milan, Italy for her research on endoscopic capsules, and Tuscany Region Award with the Gonfalon di Argento, I'm sorry, yes, one of the best 10 young talents of the region, and the KUKA Award for surgery. And she will give a technical keynote speech on training of medical tasks from simulation to simulators. Ariana.
Okay, thank you so much. I try to go in full screen. Maybe it's better. Okay, sorry. Maybe it's better to share just the
slides, yeah.
Yes, just the slides.
Great.
Yeah, but I cannot. Sorry, because I have all the faces in my.
Oh.
Yeah.
So your cursor is somewhere
okay.
there. You know?
Okay.
Yeah.
It's bottom right corner.
Yes.
Yeah. Okay. Yeah, that's right.
Okay, so thank you very much, Trish, for this introduction, and congratulations to you and all the organizers. It is a very unusual and very informative workshop. Thank you very much. So the title of my talk today is Training of Medical Tasks from Simulation to Simulators. This is something that normally it's the first time that I present this stuff all together, because we arrived to work on simulators in the last years by putting together different efforts and also different disciplines in competence. So first of all, simulation. What is a simulation? Simulation comes from Latin, simulationem or simulatio. This is the term. And there is something bad, let's say, behind the word. This is something related to imitation, false show, hypocrisy. But in any case, by doing simulation, you have the opportunity to replace one dangerous activity by preparing a similar activity in a non-dangerous environment. So there is nothing bad behind. This is not true, but this is not bad. So the history of modern simulation is is not recent. So medical simulation has been practiced for centuries, and you can see here some example of very, very early mannequin for simulation in medicine. And what we can say is that the modern medical simulation is the result of many advancements in technology and education in the 20th century. And especially with the birth of robotic surgery, we have assisted to an analogy between simulation of our airplane for avionic application and simulation in the surgical room. And also nowadays, there are some processes or there are some phases of the learning process that are indicated in the same way and with the same process and evolution in the two fields. So here you can see, just to get familiar, even if the workshop was wonderful in this regard. So you can see some example. In the first case, this is a commercial example, the SimNewB, for simulating a birth, a delivery, and so the first thing to do with a newborn. And the second case, and second movie, this is a summary movie coming from Japan. It's the Bionic Humanoid project. I have to say that I was really impressed by this huge project in Japan, started in Japan several years ago, because with the name Bionic Humanoids, you think about a traditional Japanese humanoid robots for doing tasks, for assistance, for entertainment. But in this case, they are fabricating this complete humanoids for training and surgery. And they are completing step by step all the different pieces of these humanoids by trying to simulate not only the anatomy, but also the physiology, putting together also tissue engineering, let's say, and simulation. And this is an issue and that I want to also approach at the end of my presentation, also to find the connection between simulation in medical practice and other fields in robotics and bioengineering. So why simulation in healthcare? It was already introduced today, but I think that the most relevant reference is this one. This is 20 years old, but this is true. Tuer is human from the Institute of Medicine. So it's estimated that 98,000 Americans die annually due to medical errors that you can that are preventable, and the cost, the relative cost, are approximately 75 billion. And more recent articles presented some years later says that this estimation is very conservative, it's very low. So for all these reasons, we find advantages in simulation because you have an alternate ways to acquire skill. Simulators are available at any time to be used, and so they are flexible for training without any patients in any condition. And we, in our small experience also during the pandemics, we had the opportunity to use the simulators for training during pandemics. It allows room for error. It is a solution for both residents and surgeons to acquire some technical skill and non-technical skill and to retain technical skill. And so basically, this is the reason why there is a growing market that was presented this morning by you, Trish, I think to remember, and that is very impressive for the different type of simulators, anatomical models, web-based simulators, so all the different families, let's say. So simulators in healthcare can be organized like that. For people approaching this field from the scratch, there is a very nice TED talk that I have reported at the end of my slide. But anyhow, we can consider the big family of simulators divided between virtual simulator and physical simulators. The virtual simulators can be organized in three families: virtual reality, augmented reality, mixed reality. While physical simulator, we have organized physical simulator between static and dynamic simulators. This is an organization that we have recently presented in a work for the ICRA transaction medical robotics and bionics. And dynamic simulator can be organized between soft robotics simulator ex vivo and biohybrid simulators. They are not rigid families, but just to get familiar and to find some organization that's very variegated field. So let's start with the virtual simulators. So virtual simulators can be totally virtual. So the users, the trainee, is fully enclosed. He or she has a synthetic experience with no sense of the real world. Augmented reality are in between. So the real world remains central to the experience, but it is enhanced by virtual details. So basically, you have a real world with some digital information overlay. And mixed reality is a combination. You have real and virtual intertwined, and you anchor virtual object to real world. So all these modalities can be used for training. I have to say that maybe virtual reality is more for education and training, while augmented reality and mixed reality are more for intraoperative help and guidance. Again, this is not a very strong distinction, but this is the trend that we assist, and also today we have some example in this direction. So one key element, one key technology for virtual reality, augmented reality, mixed reality for training medical task, the key technology is the end-mounted display. There are several types of end-mounted displays that you can find commercially. These are just some examples. The market of this special interface to the virtual environment is huge. Approximately 5 billion markets are expected within the next decade. And they are used for intraoperative education. They are used in two ways. The first way is this one: an attending physician wears the HMD while operating, and the resulting video stream are visible in real time to the trainees for teaching. But you can use also in the opposite way, so the trainee can wear the HMD during the operation or during a simulation, and the trainer views the video stream and photographs for evaluation. This can be done in real time, but also in a distant position. That is, again, very good. We experienced that it is very good in this period of pandemic. But how to build the virtual environment? Because a simulation is a good simulation if the virtual environment is very close to the real environment. So you have to start all the time from patient images and to make a 3D model by volumetric rendering and segmentation. So real patient image is the first step. Second step is segmentation and classification in order to obtain information about the size, the shape of the organs or of the system. And finally, you have a data fusion with registration. In this way, you can have also a virtual patient that is customized on the real patient. And this can be done also for organs with some pathologies, changing, for example, the anatomy of the organs. Virtual reality simulators for surgical training are very variegated. Nowadays, basically for all the different specialties, you can find some specific module for surgical training, for traditional laparoscopy or for robotic surgery. This is an example of 9 different specialties. And these are some movies, so you can use virtual reality, some movies coming from companies producing virtual reality simulators. So you can use virtual reality simulators for training specific essential technical skills, for example, grasping, pegging all, very suturing or clipping, as in the first movie, or for simulating a full surgical procedure, or for having a full immersion experience in the operating room. In this case, you can also assess or train some non-technical skill more related to the overall environment. Just to make a more concrete example, this is the hysterectomy module for the Da Vinci system. This is specifically developed for the hysterectomy procedures, and you can immediately understand how much is important also all the biomechanical simulation for rendering some for rendering some specific response of the tissue, or for helping the trainees to be guided during dissection, as in this case. These are some other examples for very delicate procedure, eye surgery and neurosurgery. You have the opportunity to use also realistic instrumentation. In this case, that is very good also for, let's say, optic perception. Eye surgery is something very complicated. There are some tasks as peeling that are very complicated. And this is maybe also the reason why the bionic humanoids that I mentioned at the beginning, one of the first pieces of the bionic humanoids was the eye, a realistic eye for training of eye surgery specialists. And in operating room experience, this movie is quite fast, but just to have an idea, you have a sort of that is moving in a real operating room, taking some tools and doing some task on the virtual patient. But thanks to augmentation that is possible in virtual simulation, you have the possibility to have an easy access to all the variables in the virtual environment. And so you can also modify the virtual environment itself online. And this is very interesting because it can pave the way towards constant and objective monitoring and feedback during learning. And this opportunity moved towards the introduction of an artificial intelligence mentor to assist the training during training. So the mentor can be a real human and expert surgeons, but the mentor, at least for some very specific technical skill, can be also virtual. Because from by making a monitoring of the learning procedure, the system can adapt and can guide the beginners to, let's say, to personalize the learning phase. This is something quite new that we are exploring also in collaboration with the Politecnico of Milano and with the PhD student Andrea Mariani, who is working very much on training augmentation. So preparing training protocols that can adapt to compensate for skill gaps, or for example, by working on autonomous or non-autonomous camera motion to assist the training during some Paginol or pick and place procedures. For more details about this specific family of training augmentation simulation based on training augmentation, I invite you to assist this presentation on June 3, Thursday. This is the presentation of a paper, Multisensory Guidance and Feedback for Simulation-Based Training of Robot-Assisted Surgery. So, in summary, which are the advantages and disadvantages of virtual simulator? For sure, advantages is that they are reusable. In a virtual world, you can reuse everything, and you can perform the same procedure many times with no additional cost. You have an objective skill assessment because the simulation environment allows to record metrics, and so you can access in an objective way an objective monitoring of the trainer's learning. The training can be very independent, so faculty does not need to be present all the time. And training, and this is important, can occur without using the operating room instrumentation, because using the OR for doing training, it's a cost for the healthcare system. And it is convenient because you don't need any specific location. And so you can use your virtual simulators also during downtime or breaks. On the other hand, the fidelity is not very good. So you have seen some examples, and so the tissue rendering is not the same as in a real tissue. And haptic feedback is often missing. This is not a major problem if you are training Da Vinci, where you have no haptic feedback anyhow, but this can be a problem. It is not suitable for all the person. there are some costs. It was mentioned by a colleague before me. So virtual simulators can be very expensive. Da Vinci is expensive. If I have to buy in the same hospital also the Da Vinci training simulator, it's an additional cost. And you need additional learning for virtual simulators, at least to understand how to control the virtual reality environment. Let's get to the second and final part of my talk, physical simulator. The second part of the story. Physical simulator are systems mimicking one or more feature of human structure by means of physical support within which the clinical staff interact during the simulation. Which are these features? Can be anatomy as first, but also physiological behavior and biomechanical properties. Normally, these simulators can be divided between bench models, as in this case, you have just a limb on the bench to do some tests, and mannequin model. In all cases, you can have high fidelity and low fidelity simulators. This classification has been used, as I mentioned, in this recent paper published this month on transaction medical robotics and bionics. So, static simulator. First of all, static simulators can move, but actuation of static simulator is not during simulation, okay? So they are simulated without real-time motion. They can be fabricated by synthetic materials. They can be sensorized or not. Normally, they are provided with a graphic user interface, and they can present real-time or a posteriori feedback. In these movies, you can see some examples of simulators, for example, for cannulation or for emergency procedures. In this field of static simulator, we have investigated very much the field of neonatology. I was fascinated by the presentation of the, I don't remember the name, sorry, but the pediatric expert, because yes, it's true, newborn children are not little adults. They have smaller dimension, but they have also less developed muscles, soft tissues, more flexible ribs. And especially if you work in neonatology with preterm babies, timing is crucial for some specific operation. You have to take care of forces and deformation because you are not allowed to generate much forces on these very delicate tissues, still in formation. And if you do some errors, and if there are some damages during the intervention, these damages can affect the whole life of the baby. And this framework, collaborating with a Center for Simulation Neonatology, we have developed a high fidelity sensorized mannequin for training the intubation. That is an emergency task for preterm babies. So starting from the reproduction of the skull, coming from CT scan, we 3D printed the skull. We sensorized all the parts in contact with the video laryngoscope that it is used for intubation, so the arc, the tongue, the epiglottis. And we sensorized also the tool that is used for introducing the tube for breathing, for helping to breathe. And we did tests with neonatologists by putting some threshold forces, threshold pressure, thanks to the help of expert neonatologists, and by making tests with beginners that have the feedback of the force that they apply on the tongue, the force that they apply on the arc of where the teeth will birth, and so on. Again, in this field, we developed also high fidelity neonatal pneumothorax simulators. Also, pneumothorax, it's a task that you need for some preterm babies, because you have to free the lung from some air under the pleura. So again, we started from the reproduction of anatomy through CT scan. We realized that the mannequin, by using materials with biomechanical properties quite close to real tissues. We used also self-healing materials to use the same simulators many times. We simulated the pneumothorax by creating 2 self-sealing and airtight chambers inside the simulator. And we generated the pneumothorax before the simulation by using 2 pumps and controlled by commercial pressure sensor. The system is very easy to be used. We tested it with residents during the pandemic. So my PhD student, Sabine, and my postdoc, Selene, were at home controlling the simulators in the hospital with this resident that were able to assess also personally, without any additional expert, the overall procedure of decompression of the lung. And the system was demonstrated to be very robust. Again, in the field of static simulators, we approached the problem of the birth. So there are many birth simulators, but it seems that it's quite complicated to understand for the trainees, which is the exposition of the baby during the delivery. So we used the traditional simulator, but we inserted some sensor, inertial sensor and electromagnetic sensor in the head of the simulated baby to present different modalities of the babies during the delivery. So the medical doctor, the expert gynecologist, can set different modalities that through a GUI, and the test can be performed for assessing a specific procedure with specific delivery modalities. So not just doing tests and putting the babies in some not reproducible manner. Dynamic simulator, the second family. In this case, you have simulators with real-time motion. So actuation is constant, active during the simulation. Again, normally you use synthetic materials or ex vivo tissues. It depends case by case. Also in this case, you can have a real-time or a posteriori feedback, and again, a GUI. What you can see here are some examples of pediatric and newborn babies for simulation with different degrees of interaction, also for, let's say, assessing the non-technical skill and to, let's say, to give the trainees a complete mood of the environment. These dynamic simulators are involved also by technologies of soft robotics. So soft robotics, utilizing some materials, elastomer, and also soft actuators, can be, soft robotics can help very much in the field of simulators, because you can simulate both physiological and pathological conditions with high flexibility and controllability. This is a new field, let's say 10 years old. So mainly at the moment we have just organ simulators. These are some examples. For example, this very nice gastric simulator with some soft actuators for reproducing the peristalsis of the stomach during digestion. Also in this field, there is a patent pending. We are developing an high fidelity adult thorax simulators for laparoscopic surgery by robots. with the diaphragm that can be moved in an active way during the operation. Again, in the field of gynecology and baby delivery, we developed also a cervix simulators. During the delivery, there are three actions: the softening of the cervix, the effacement of the cervix, that is a shortage of the cervix, and the dilation. So we used the granular jamming, shape memory actuators, and traditional motors to, let's say, simulate all these three phases. And we fabricated a simulator that is not mimicking the cervix at all, but you can combine, as gynecologists asked us, to assess the different phases of the labor. And you have a GUI that can be used specifically for testing the dilation, for testing the softness, and so on. Finally, ex vivo simulators. Ex vivo simulators are fabricated by using fresh tissue, just explanted from animals. In this way, you have not to take care about the anatomy, but of the preservation of the tissue. When you take a tissue from an animal, so it's a different story, because in some cases, the simulators are very good only if they are perfused. This is an example of a human porcine respiratory model for preclinical studies, starting from real lungs that are reperfused with air. And finally, we have biohybrid simulators. In this case, you have a combination of organic tissue and synthetic robotic components with actuation. There are very nice work by Alain Roche in MIT reproducing the Earth thanks to biohybrid simulation. Another example reproducing a lung, in this case, is coming from Austria. All this stuff are just for specific organs. There are not yet complete system, but they are very good example if you want to reproduce also the physiology. So let's go to the final slide of my talk. So originally for training, the paradigmatic teaching was see one, do one, teach one. I think that we can see that this is something no more sustainable. So you need more quality. For sure, robotics and artificial intelligence can improve the process of learning. This is especially true for virtual simulator. Novel paradigms in robotics materials, tissue engineering solution can boost the field of simulators and simulation. And last but not least, artificial organs and medical surgical training. They can cooperate in a synergistic combination. Quite 3 years ago, together with Matteo Cianchetti, that Trish knows very well, we prepared the paper for Nature Review Materials, assessing the biomimicry and biocompatibility of some materials. And you can see that body simulators and artificial organs are at the same level of biomimicry, even if with different level of biocompatibility. And recently, I tried to find out some links between the two fields, and there's a short tutorial for APL bioengineering, implantable biorobotic organs. Thank you very much for your attention. I'd like to thank the people behind this work. Selene Tonierelli, postdoc, working on physical simulator together with Sabina Maglio, PhD student, and Andrea Mariani, PhD student, working on virtual reality simulator. Thank you very much.
Thank you very much, Ariana. It was a wonderful talk. I mean, so many new things I didn't know happening in your lab. So Ariana, please stay. And then now I'll invite all the morning session speakers. Professor Kazuo Kikuchi, Honglian Ren, Dan Tiruchelvam, Bing Fang, Masayo Yamazaki, and Mustafa Ern to unmute your mics So we go to this ideation session. So in this ideation session, you can ask each other questions, you show each other's talks, and then maybe I can pose a kind of opening, very open-ended questions. I'm really kind of fascinated by the increasing robotics capabilities, but the medical side is not that simple, right? To replace a real patient by a robotic patient, especially when it comes to multimodal sensory integration. So, medical practitioners, they not just see things, they feel things, and then they hear things. And then the whole, sensory modalities are involved, but sometimes sometimes engineers overthink about it. For example, Da Vinci surgery, it doesn't give haptic feedback, but they do very well with just visual feedback. We think that haptic feedback is important, and then sometimes in physiology or physical examination, auditory feedback is very important, but we don't think that auditory feedback, engineers don't think auditory feedback is important of pain expressions and vocalizations, right? So these things can be missing between engineers and doctors. Maybe the medical side of the speakers can first give us some kind of insights about how you depend on this kind of feedback that the roboticist should pay attention to. And then the follow-up thing about that is performance feedback to the beginner. So let's say if the robot gives a very advanced level of feedback, like quantification, saying, okay, you're bad, compared to a real expert, that means it is going to kind of, be kind of overwhelming to the beginner. So maybe we should give performance feedback in a graduated way, right? So you pass the first level, okay, so that's good enough. Then we go to the second level of complexity or hardness of the task, and then that kind of thing. So can we know more about this kind of thing? Because like we don't know how medical school is running these things. First, if the medical side can talk about it, and then roboticist can chip in. Yeah.
So Sranta, I don't know whether you can hear me.
Yeah, I can hear you.
Yeah, fine. Yeah. So on the first point about the haptic feedback and that sort of thing, it's interesting. The human beings are very adaptable. So yes, we all say, all right, there's not much feedback from the Da Vinci, but we can still do it. However, if you were to add haptic feedback and auditory feedback, these things add more and more, right? So an example is that if you got that extra little bit of haptic feedback, it contributes to what you can see with your eyes. And then if you were getting auditory feedback, like for example, you were straying outside of or into a dangerous area and you get an alarm signal or something like that, they all contribute. So I think the more the better, but the problem is obviously there's only so complex you could make these things at this point. On the second point about the feedback, yes, I agree, it is graded feedback. So in fact, on the simulators, there are often levels. So beginner, medium, advanced, etc. But the way education is moving, whether it's medical education or otherwise, is individually based learning where the learner can scale up as necessary. And I think that's very important, right? Because, when I've taught trainees, there are those ones who will take 1/3 or 1/5 the time to learn something that somebody else will do, right? So, and in fact, there are often these ones who can almost teach themselves. And then at the other end, you've got people who need repetitive, repeated, and they'll never get to the same level. They'll still be okay in the end. So yeah, it's a combination of those things. So, yeah.
Great. Right. Thanks, Dan. Any other comments on the medicals? If there are no, maybe the panel can ask each other questions, so to clarify things more. Either way is fine. The medical side asking questions from the engineers. And
if I may say a few things on the discussion you had, I think one of the main challenges for training is provision of feedback. I think as far as I understand, this also goes in line with Dan has just mentioned. Which also supports individualized way of improvement or training. So actually, people who are working on training are mostly focusing on assessment. And many of the simulators, when they say that they provide feedback, actually they perform small scale or short-term assessments, and they give the result of this assessment as a feedback. So somebody does something, and then the system says, okay, you passed level 1. Then you start working on level 2. Actually saying you passed level 1 is not provision of feedback. It is an assessment. So whether the person passed level 1 or not. So assessment is important. It is challenging. It is difficult. That is like that. However, it is not really feedback. I think what we need for training is a provision of feedback in such sense when when the trainee does a movement, make an action, our system should be able to understand whether the person is doing the right thing or something wrong. And if the person is doing wrong, immediately at that time, the system should be able to say that, hey, you are doing wrong, and this is the way how to do it in a correct way, and show it, and provide the knowledge, information to do it in the right way. So this is what happens when you have a supervisor, when a professional surgeon watching you and telling you what to do. So the training systems should provide this. And I believe the current state of artificial intelligence, vision processing, machine intelligence, and robotic systems allow this. We can develop, actually in my lab, we have developed prototypes of this kind of things in that direction. So in real time, we can detect what the person is doing, and we can have a repository of how things should be done by observing, by analyzing how professionals are doing. And in real time, we can bring those as samples to the trainees in the monitor with some visual, audio, and various feedback forms. I think if we can equip simulators, all forms of simulators, with this kind of mechanism, I think that will be a very significant step forward to allow trainees to educate or to train themselves with a machine or system.
Thank you. And yeah, that's a fascinating idea to have an artificial intelligence supervisor or assessor, so who can give not just good or bad judgments, like to show what is the right way to do things, right? That's very interesting. So any other panel to panel questions?
Can I ask a question? So those of you that are familiar with the Da Vinci system, it's essentially a cable drive system with shafts. There are 4 little wheels on the end of each one, and that's rotated, and then the end is moved. Why can't, and that's been around for a while now, right? So it's been around for a long time. Why haven't we moved past that kind of system from an engineering point of view?
Maybe Ariana might be. Ariana, your mic is muted.
Yes, Trish, can you repeat, because
so Dan's question was like, you know, this Da Vinci robot has been there for a while, and then it is just a cable-driven, like, you know, burden cable-driven thing with we have some degrees of freedom and the gripper, right? So why are things not moving from that, right? So that's a question.
This is not related to simulation, so I understood correctly. Thank you, anyhow, Trish, for answering. Okay, the reasons are many. One of the first is that the Da Vinci system was protected by very powerful patents from at the beginning. So there were other examples of robots moving in the same direction, but there was a problem of patent. I remember an example in several examples in USA, one in Canada, another one in Korea. But in the meantime, there was this problem of the patents, and once the patents expired, it was too late in a sense, because Da Vinci was already very, very, very spread. For sure, this is very good for laparoscopy. There is an excellent ergonomics, and now there are platforms for training robotic surgery with Da Vinci. So there is a combination of things, and another consideration is that medical robots you cannot go on the web and buying medical robots. There is the healthcare system, there are some processes. So it's different from developing, for example, a robot for edutainment. If there are 10 companies with different robots for edutainment, you go on the web on Amazon and you buy it. But for medical robotics, it's a different story. What I can say is that there is a trend towards more handheld robots and cooperative robots for surgery. A little bit more patient side together with the medical doctor, and also less expensive. But the reason, in my opinion, it's the combination of patent, to be afraid of patent infringement, in the meantime having the time to grow up.
Yeah, exactly. I mean, lots of attempts are going on. The entire surgical robotics community is doing wonderful innovations every year. And then, I mean, in this conference itself, you will see how many papers have been presented about. So, but the commercialization has a big regulation and legal barrier. So that is something everybody is facing now.
Somebody told me that the number of engineers working in intuitive is not so far away the number of legal people. So just to have an idea that you cannot, let's say, okay, we put together our efforts and we build up the company for selling a robot for medical application.
Yeah. So, I mean, we had another workshop. Casper organized a surgical robotics workshop a couple of weeks ago, and then Pierre, right? So Pierre DuPont. So who Pierre or what? Who? His company, Ariana. So the continuum, the pre-shaped.
Bob Webster.
Oh yeah, yeah. So Bob Webster, right? So see, I mean, maybe Casper can say like the challenges he's facing to get that robot out. So Casper, do you have anything to contribute?
Yeah, I can just comment on that. I mean, that is definitely a big issue, and Ariana mentioned patent lawyers, teams of patent lawyers in companies just to look at that aspect. I mean, certification, of course, is on top of it. So it's a long, difficult process especially for medical systems, medical robots to be established and to get into clinical use. And I suppose the competition is fierce between these different companies that are, trying to get a slice of the market. Good news is obviously, Trish and Ariana, you said it, the market is increasing, so hopefully there is a niche for everyone. But I think there is definitely great interest in or need to create new systems, and if you have if you have the stamina, then this may be your area, for you a good area to go into. I wanted to say something slightly different, but also kind of related. So first of all, thanks for all the presentations. I mean, I was also super impressed by what is happening already on the simulator front. What I wanted to ask is, maybe it's too early to ask that question, but is there also a possibility to move to some kind of standardization? Because at the moment, many things are moving in many different directions. Great things are being developed, but shouldn't there be also at some point an attempt be taken to bring things together and standardize?
Yeah.
And that might go against exactly what companies are about, having their own thing and their own patterns and kill everyone else in the market. But I think it would be beneficial for the patient. I mean, obviously the same applies also to the development of actual surgical systems. But yeah, and so maybe I'm just dreaming aloud here.
The panel, anybody from the panel about standardization? So it can be, I mean, even benchmarking, right? So like it's very, very useful to compare our results. If there's a set of benchmarks in each, let's say laryngoscope, this intubation procedure. So if there is a standardized set of benchmarks, graduated set of benchmarks, and then we can all compare our results. So why are we not having that, right? So that's the question.
Yeah, I think it's a good idea, Trish. Let's start with a benchmarking effort before we go to standardization.
Yeah, exactly. Anybody in the panel, any views about it?
I am not a medical doctor, but for example, for test laparoscopic skill, there are the FLS that are considered the fundamental laparoscopic skill assessment. In this case, there is a sort of standardization. I don't know if there is something similar for virtual simulators, maybe not. And for dynamic or hybrid simulator, this is a new field.
Yeah.
Well, I personally got interested in remote training or virtual simulators because during the pandemic, it prevents sometimes students from doing their clinical study in the hospital. For example, one student was found to be COVID-19 positive, then all the students were forbidden to enter the hospital. Then if we have remote training system, that would help students. So do you think the pandemic changed the direction of the robotic medical training system look forward? Do you think that pandemic had changed the direction?
Anybody in the panel? I mean, I have my own views, but I think, like anybody, please feel free to chip in. The space here, yeah.
Just, I mean, I think it's too early to say something. I mean, more long term, because I mean the pandemic was very, was quite far reaching. Let's put it like that. but on the other hand, very short. I mean, we're talking only about 1 year plus. So I think that is not enough time to make really major differences. But I think there are real opportunities, and I also believe researchers taking those on board, and they're learning, and they are trying to create new systems that take that into consideration. And there have been quite a number of conferences and special issues. I mean, for example, we had a special issue on COVID-related robots. That was in RAM, the Robotics and Automation magazine of IEEE. And so I think that there is an interest there. And I mean, my personal hope would be that these techniques that have been developed over this short period would remain, or that we take from that we learn from best practice there and keep that on board to be prepared for the future. But difficult now to to foresee how things will develop. That's my view.
I think that is Masayo. I think that's a very good question, timely, because we felt the need for remote education in many fields. Like, I mean, in engineering, we can do a deliver small pack of electronics so that students can do some circuits at home and then do the Zoom teaching or Teams teaching. But in medicine, you need a patient, right? So in clinical, so I think then shipping an entire robotic patient is not possible if it is physical. This really opened up the need to have minimum hardware augmented reality solutions in the future. Right, so that is something we are working on. Right, so you have a virtual reality robot, and then basically you have a soft robotic mouse where you can get the haptic feedback, and then that is intelligent enough to give you camouflage tissue conditions. So that is something we are working on in the Robopatient project. So I feel like you saw that trend of market opportunities also growing, and then it is a very balanced growth of virtual solutions and physical solutions. So my guess is that in the future it'll continue towards augmented reality solutions, a combination of virtual, web-based, cloud-based solutions, and minimum hardware, portable hardware. So that could be the future the robotics community can think of. So as a clinician, what do you think about it, Masayo?
Well, I was really surprised to see the market is really growing, while here in the Department of Pediatrics, we do not have enough training system. I thought that there are two reasons behind that situation. One is that there are only limited numbers of doctors who had interest in medical training system. So while we do not have enough training system here in our hospital, I know that in some other institute, they installed very good training system. So if they have some doctors who has interest in training, they try to install the training system. And another point is maybe the cost. And I was happy to know that you are trying to produce the less expensive techniques that would help us.
Yes, so that is extremely important, the cost. So that is why I think augmented reality solutions would be useful, because it is just a cloud-based web solution. You don't have to buy that. You just log it in, and then even the hardware can be rented for a lesson. So you just post that hardware. We do it already. We just lab in a box type of thing idea. So a small microscope, oscilloscope and then some breadboards and things like that, and that is enough for the students to get going. So that is an engineering challenge. And then I just wanted to check if the clinicians are happy about that. So I think it's a good news that you are looking forward to that kind of solutions. Any other thoughts about?
I don't have the much experience in that, but I'm talking about the standardization from Casper, and also the I was thinking about it as the end user is the surgeons, right? If we want to build a whole surgical robots, the surgeons need to use it. And if we have many different options, it might be harder to choose or sell or keep doing training for different devices to masterize the robots. I remember I had a training in a hospital for a week, and one of the new technologies being introduced, and I remember the doctors weren't very comfortable with it. So I think new technologies always will take time till the surgeons got used to it. So I think standardization might reduce this problem, where we know like there will be one controlling system, and I don't know, every company jump in and develop some part of it rather than designing totally different robots. And that's where it makes it uncomfortable maybe for the end users to choose which robots, and makes it expensive, and all so on and so forth. So I think, I don't know, this is maybe for clinician, maybe, I don't know, maybe Dan knows more about that. Yeah.
So I think what you're saying is correct, that when you're introducing new technology, it can be quite difficult. So in general, the medical profession is very conservative, right? Because the risks are high in terms of just adopting something new and trialing it. And I think I might have mentioned this once previously, but if you look at the lifespan of a surgeon, by the time they're in their 60s, they're very unlikely to be picking up some new technology and techniques, right? And then probably in their 30s, they're still sort of, finding their feet. Okay, so it's really that cohort, which is actually quite small then, which is in the 40s and 50s, who are going to be the adopters of the new technology. So this is why I think whenever anything comes in new in medicine, you'll get the 30-year-old group not that keen, the 60-year-old group not that keen, and then you've got this other group in the middle that would pick it up. And it does take a lot of time and effort. I mean, I think if I look at the way we introduced new technology, it's time consuming, it's difficult at the beginning, it's stressful, it's, all that sort of stuff. So human nature tends to default to what they find easier. So if there is some way, as you were just talking about, with standardizing some parts of it, that may make it a little easier. The only downside to the standardization, I've got to say, is that maybe standardization stifles innovation. Don't know.
Yeah, that's also true. Yeah. I mean, standardization with options, like, for example, standardization for at least, let's say, some modalities of feedback, right? So if you give only visual feedback, this is the standard. And then if you add another haptic, let's say auditory feedback, this. So it's not a single standard, but like a standard with graduation, and then room for complexity, different levels, is something like. I mean, it's like, let's say, flight simulators, right? You have different flight simulators. Not everything is a Airbus or Boeing 777 simulator. So can we have that kind of standardization in medicine? But the problem is medicine itself is evolving with the introduction of technology. So I think this is why this dialogue is super important, right? So engineers and doctors continuously talking to each other and then understanding each other. Then the standards will naturally evolve.
I mean, one thing I can say is that if you look at, yes, Da Vinci has permeated into a lot of areas, but if you look at laparoscopic surgery, if you has it gotten where it could? The answer is no. And one of the negatives is it's just not fast enough. Like, for example, I was operating today, and even, you know, when you're quick at doing stuff, the robot still takes probably, you know, twice as long to, you know, 1.5 twice as time as long, just to do what you would standardly do, but depending on what specialty you're in and so on, right? So I think the speed of the robot is one thing that could improve.
Right.
I think it's very interesting to see and to hear from the clinical side the challenges that you have faced, and I'm also really curious to know, like for example, with the challenge that the resistance between among the the clinician side, what are the challenges, or how do you actually, for the technical experts like the roboticists who are trying to introduce like new ideas and technologies to these medical experts, like how do you overcome this challenge, and how do you go about introducing these new technologies into the field, and study collaborations, and get them on board for trainings and stuff? So it would be nice to hear from the technical experts. Would anyone like to talk about this? Like maybe Professor Ren, do you have anything to share?
Well, thanks for the question. I'm not an expert in this simulator part. So I myself developed a lot of surgical robotic system, some of the artificial intelligence sensors. We're trying to improve the procedure. I think to add on to Dr. Dam's comments, so perhaps we, if we can do something that to increase efficiency. So at this moment, some procedures specialization are still slow, even we have the robotic system available. So meaning that we can still do things better. So Da Vinci system has been there for many years. There's still some gap forward we can fill, increase the speed, make it more intelligence, more sensing feedback. So if we can do as engineers, so my personal feeling is if we can do something useful for the clinicians, so we can definitely have higher chance to engage the clinical collaborator. So especially during the pandemic, we know the clinicians are very important. So we as engineers, as for myself, I try to make whatever my communication to my clinical collaborators more effective. If I can take 1 minute, I don't take 2 minutes. So they are very important. So I think we can still engage them if we show something that is really, really something they need. We can do something, for example, we can increase the precision in micron level, which is not possible for most of the surgeons. I think that, or we can sense for example, the interaction force in millinewton level for example, for eye procedure, for neural procedure, then the surgeon gonna have much higher interest. I think at engineer, we want to do something that can complement or enhance the current capability. So that could be certainly one way to increase the efficiency and increase the chance of collaboration. And I may also have another comments for the standardization. So at this moment, it's very a lot of comments from our panel. So I would say, or maybe a little bit supplementary comments. So the technology is evolving. If you look at, for example, the wireless communication, the 3G, 4G, 5G, the standards is also evolving. And for either simulators or surgical robotics, I believe, along the way, the new technologies, new clinical needs is coming out, and our standard or standardization also need to evolve. So just my rough comments. Yeah.
Thank you very much, Hanglin. Like about your sampling robot, teleoperated robot. So, what kind of regulatory barriers did you have to face? Was it implemented on real patients, or did you have any like regulatory legal barriers to that?
So I assume you're referring to the swab collection.
Yes, sampling.
Yeah. Okay. Well, at this moment, we do internal in-house testing. We just need to get the volunteer consent and some of the internal IRB clearance. Of course, if you want to move on to, for example, more larger scale, either clinical trial, or maybe we really want to push to the market, we certainly need to get a lot of regulatory approval. It always takes time. So I'm not the only one doing that. I see a few other groups also developing the swab collection robot. I think, as far as I know, most of them are probably, almost all of them, if I say it in a more aggressive way, are in the testing stage. So it's really, it's really a hurdle. So that's probably also one of the reasons why many technology, robotics, AI sensing technology are slow to penetrate into the operating theater. So that's certainly the reason.
Right. Okay. Yeah. I mean, finally, it ends up in an insurance problem, a legal problem.
Yeah, that's right. Yeah. So the legal person also play an important role.
Exactly. That's important. I think engaging them right from the beginning might be an approach in the future. So we were, Casper and Ariana and we were in that workshop where Bob Webster presented his translation activities of this surgical robot. He has a lawyer in the director board. So that's very important, I think. A good lesson to all of us. Any other questions? We have about 9 minutes left.
Okay. I have one. I have one question also for Professor Deng. So that if we want to add haptic feedback to medical training system, we need to have the haptic sensing part and also the haptic. And so which one do you think poses more challenges for a medical training system and also for robot-assisted minimally invasive surgery? Haptic sensing part or the haptic feedback part?
I cannot give a definite answer, and I would say from my experience, they are both challenging. So which one is more challenging perhaps is depend on which procedure we're working on. Let's say if you're working on intraocular procedure, eye procedure, and the space is really limited and confined, the adding any additional sensing components is super challenging. Well, at this moment, if you have outside haptic, master or surgeon side instrument, that perhaps we don't have that much space constraint and relatively easier to develop. Well, if you change it to another way around, if you work on perhaps abdominal area, a larger area, and we have sufficient space, And then if you want to add in a little bit sensing component, the challenges is not that significant. So I would say perhaps it's also depend on the procedure, depend on the location of the target, and also depend on in which level, either resolution, temporal resolution, spatial resolution requirement, and also the human perception, well, it's not a single disciplinary challenges, it's really multidisciplinary challenges. But Eugene's good question, that's, I think, very important for the people from different fields, engineering, clinician, multiple disciplinary researchers to work together to resolve those challenges.
Mm-hmm. Yeah, very true. Any other questions?
I will ask a question. I think this is for both the clinicians and technicians as well. So we saw different approach or different surgery robot using different manipulators. So DaVinci has their own manipulators. We saw in Professor Sophie Erden's training platform. They're also using the phantom manipulating systems, and also for Professor Ren's setup, they have a different approach in controlling the effector of the robot. I was wondering, like, for the general training purpose in medical school, do you think it's good for the trainee to learn a general approach that they can transfer the knowledge from one platform to another platform? And if so, what do you think are the most important factors of this general learning approach? Is that going to be the awareness of those the temporal or space warping, or it has to be the hand-eye coordination, or it's be the diagnosing based on this 2D image? Or what's your idea?
Okay, thanks for the great question. Well, it's certainly challenging. So I would think about the question in this way: the multiple system development is really to push the technology forward, especially for research laboratories, because at this moment, even we see the DaVinci system has been very popular. We still have many, many challenges, still have many, many clinical needs, as we have seen, deep inside the brain, deep inside the eye. So there's still many challenges there. And also at this moment for the respiratory disease, the lung biopsy. So all these require new technology breakthrough so that we can overcome the current boundaries, so we can do that better. So, and then this comes to the training part. It's really the training at this moment. I'm not an expert, but I can feel that people are providing training mostly based on what systems are available in the clinical setup. So maybe the expert and researcher here in robotic simulator, robotic patient can have a better say for that. I think standardization or make that robotic patient simulation can be transferable to different generation of surgical manipulator could also be a clinical need, or could be also training need. One more thing from my part, maybe, as I mentioned in my talk, we can allow a robotic system to learn from experts. Let's say I have experienced surgeon that have done a lot of surgery. We record the videos, or we record the key parameters, and we ask the robot to learn that. And those experience can hopefully in the future, if you have more advanced technology, we can transfer that to the newer generation of manipulator. It's a hardware domain adaptation, perhaps. I just coined a name for that. So that's just my very preliminary thoughts for that. Perhaps our other colleagues and peers have more comments.
Lawrence, we have another question from Lawrence.
Oh yeah, so Professor Kazuo-Kyuji, do you have any comments or any observations on Professor Bin Fan?
Well, actually, I have a question to the medical doctor. Actually, direct question. Medical doctors need robotic patients or not? compare with a real patient or just mannequin. So, you really need a robotic patient or not?
Or not? Yeah, that's a great question. Yeah. Dan, are you around? Oh yeah, yeah.
So I think we can get by without them, but I still think they'll be helpful. Okay, because as I mentioned before, training opportunities are going down, and you see, if you look at 30 or 40 years ago, I think the general public was probably more tolerant of training than they are now, meaning that everybody demands perfection. Okay, so if you need to give perfection, then you want to minimize the amount of potential harm or risk. So the more somebody can practice on something with minimal risk, the better. So in short, yes, I think we need robotic patients, and I think they will be very helpful for training.
Great. Masaya?
Yes. I also think that we need robotic patients, and I think there would be growing demand for robotic system because in pediatric field, they also weigh more on the ethical problems. So we want to reduce the pain we put on the child. So in that sense, residents or students are really limited to do the invasive procedures like we used to do in the past. So I believe that robotic system will help students and residents train effectively.
Yes, that's great to hear that, and there's a need for what we are trying to do, this whole robotics community. So with that, I can.
We have one question. You can.
One question. Is it okay?
Yes. It's a chat.
What's the question?
Yes, sir. Well, yeah, I mean, it's in the chat, so I can read it out. So this is from Zhongliang Jiang from our audience. And he commented that he's actually personally very interested in the automation system and also hope this could help doctors for better and precise operations. However, if we go further to try to make such a system as a product used in clinical routine, do you see any way to how to better divide the responsibility for the robotic system and the doctor? Or do you think this is not the real direction to go? We do need to limit the automation level for avoiding any kind of risk during the operation.
That's a great question. I think there were a few answers in the talks themselves. But any of the keynote speakers, do you have any? I think Erden, you had some ideas about it, right? Do you want to talk about it?
Trish, I have not an answer, but I was putting something in the chat. I remember that there was a nice short paper on science robotics a few years ago about the level of autonomy of robots in surgery, with different level, task autonomy, and for example, suturing, up to the eye level. And I have no answer, and I am not an expert, but there was a quite challenging consideration at the end. How to assess if a medical doctor is a good medical doctor. Normally, there is a sort of, let's say, society, for example, the Society of International Society of Endoscopic Surgery, and so they make an evaluation. They say, okay, this young doctor is a good doctor. But if there are, so this is a sort of certification. We have not CE mark, we have not FDA. And what about medical robots? They should be certified by other robots. So I have no question. This was a real challenging question, but if we go at the high level of autonomy, so it's difficult to certify a robot that is autonomous.
Exactly. I think, I mean, autonomy is great. Robotic autonomy is great if it empowers the human. It is not really, to overtake the human. If the surgeons, let's say, the hand is trembling, like, let's say a very senior old surgeon, it is okay to have autonomy to do, tremor cancellation. So on the robot side, so that the surgeon's real skills can come in. And then, like I think Sophie Erden also talked about it. Like if the and Dan at some point said, if the doctor is going to make a mistake, it is okay to have autonomy on the robot side to alert them and to correct them, right? Help them to come back to the right path, those things. So as far as it is good for the patient and it is empowering the surgeon, then I think the autonomy is a good thing to have on the robot side. But it is debatable. I'm fully aware of that. So with that, let's conclude this session. It's wonderful. We had a nice discussion, very open 1 hour discussion. And Professor Ariana Menchasi, Professor Kazu Gihichi, Professor Onlien Rang, Dr. Dan Tirsholom, Professor Bing Fang, Dr. Masayo Yamazaki, and Professor Mustafa Erden. Thank you very much for sharing your valuable thoughts, and then for the nice discussion. And then we go to the lunch and poster session from onwards, and then keep now each other, keep the chat going, right? The conversations going, and then let's hope we will do something useful to the clinicians. Thank you very much.
Sure, thank you for organizing this.
Thank you.
Thank you very much.
Thank you.
Thank you.
Thank you very much, guys, for attending the morning session. We will now be starting our lunchtime break / poster sessions. And we'll have hopefully two presenters showing their submission, their accepted paper at our workshop. And our first presenter would be, let me see, Chauna Chen. Are you here?
Yes, I'm here.
Okay, would you like to start?
Do you play the video or I will?
Yeah. Selena, are we playing, or do we want the presenter to play?
Yeah.
I think if you can play the video, it's fine for me.
Yeah.
Okay. Yeah.
Jacob, yes. I need the YouTube. Yeah.
I don't have the video link. Selena, can you play it?
Yeah, hold on.
Thanks.
Just give me 1 second. Yeah, hold on. Can you see my screen?
Yeah.
Can you hear the sound as well? No.
Not enough. So I think before sharing, you had to click.
Yeah. Okay. Yeah. Just this. Where is it?
You click on share screen and it's the bottom left tick. It's the tick box on the bottom left.
Yeah. Okay. Yeah. Share some. Right.
Donna Chen, a level home research fellow at the University of Glasgow. Yeah. Today, I will show how we can model variations in dynamic facial expressions of pain using a data-driven psychophysical approach. An essential skill in medical professionals is to accurately detect the facial expression of pain across a variety of patients. Medical training simulators such as Robopatient can be used to assist such training. However, it's important that the simulators are able to express the natural variations of the facial expressions to avoid overfitting. Here, we model the variations using a data-driven approach and subjective human perception. On each trial, a face movement generator randomly samples and dynamically generates a subset of action units and combines them to create a random facial animation. The participant categorized the facial animation as representing pain or not and rated its intensity. Therefore, on each trial, we can agnostically capture the dynamic facial movements that represent pain to an individual. 40 participants in each of the two controls each completed 3,600 such trials. We then measure the statistical relationship between the facial movements presented on each trial and the participants' responses to produce a statistically robust dynamic facial expression model for each individual participant, as shown here. Importantly, deriving models per participant allow us to estimate the population variance and identify individuals with atypical performance. We then measure the variation by computing the relative exclusiveness of each action unit to the gender and the cultural group using mutual information. Results reveal a common set of core action units and the cultural specific and gender specific accents, including mouth stretch in East Asian model and the unilateral nostril depressor in male models. Here, we show that our data-driven psychophysical methods and per-participant modeling approach can formally characterize the variations. Our models are also directly transferable to medical training simulators, which we anticipate will contribute to improving training performance. Thank you for your attention.
Okay, thank you very much for the poster submission. And we have our second presenter, Luke Holland. And Luke, would you like to present your own video, or would you like us to play the video from YouTube?
You can just play the video of YouTube, I think, if you've got it there.
Okay.
Or I can just do the presentation, whatever's easiest.
I mean, if you don't mind, you can do the presentation if you want to.
Yeah, let's do that because I've prepped it already. So
okay.
All right, so it's a little bit different to some of the other RoPat stuff, but hopefully, you know, with the clinicians and the engineers, both people are going to find it interesting. Let's just share my screen. Okay, can you see that? Okay.
Yeah.
Great. All right, so this is a proposal of a method to transfer emotional meaning through abstract visualizations. Yes. Okay, so correct understanding and efficient recordings of a patient's emotional state is critical to healthcare. However, a significant segment of that emotional information is passed and recorded using text-based methods. For example, text-based consultations and patient histories. Now, physicians then need to be able to correctly and confidently decode the emotional information concealed within those written messages. However, studies have shown that there is high inter-subject variability when it comes to our shared understanding of emotive vocabulary, namely that different people often extract different emotive meanings from the same words. How can we add emotional information to text-based messages? One heavily studied method of emotional transfer is through abstract visualizations. Now, abstract visuals are very powerful at effectively and efficiently conveying multidimensional data sets, as users can comprehend multiple visual parameters simultaneously without pre-existing contextual associations that can warp our understanding of the words. Now, this paper proposes an initial prototype of an algorithm that takes a psychological model of emotions, the dimensional model, and produces effective abstract visualizations in real time using Unity VXF graph. Now, these visuals aim to serve as a non-lexical emotive language that can efficiently transfer multidimensional information between people. So the algorithm designed takes in emotional information in the form of a dimensional model and then converts to the visual space by interpolating between data points whose parameters were designed in accordance with the literature. Now, the novelty of this study is that it uses a single model to map to all emotion states and does so in a way that incorporates both discrete and dimensional emotion properties. So as with most effective computing models, the emotional space uses the dimensional model of emotion, which allows emotional inputs to be numerical. Now, 3 parameters are used that facilitate the description of the emotions. So that's valence, arousal, and dominance. So the abstract visualizations are then constructed using a particle system rendered in real time using Unity VXF graph. Dimensional emotion parameters can be inputted, and the model will output several visual parameters that determine the appearance of the visual. So the key mission behind this study was to explore the variation in participants' perception of the abstract visuals alongside the dimensional emotion parameters. So the metrics of comparison were how closely people agreed on the effective meaning of the emotive words, and this is what we were comparing the visualizations to. So this data is taken from a 2012 study, and that showed the participants emotive words and then asked them to note their perceived dimensional emotion parameters. And then we use the same method to analyze the abstract visualizations. So analysis of the data reveals that there's significantly greater agreement amongst participants when evaluating the emotion being transferred by the abstract visuals compared to the emotive words. The improvements are mainly along the arousal and dominance parameters, indicating that these are the ones that may be better understood visually. So studies over the last few weeks we've been trying to incorporate this within text-based messaging systems, and using sender-receiver pairs have been analyzing the emotional comprehension gains that you can get from in-text-based messages by the incorporation of these visuals. And that's basically shown the same thing, which is, in the presence of some of these visuals, you actually get better emotional comprehension of text-based messages. So this was just an initial study. It's basically demonstrated that abstract visuals can be used to intuitively understand complex emotional data sets to a degree of precision which outstrips emotive words. Now, future work is going to investigate the logistical methods of practically combining text and visualizations. How can this actually be used in a clinical or commercial setting? And whilst this study has focused on emotional communication within text-based settings, emotional transfer using abstract visuals is not limited to that. It could be used as a novel method to aid expression in emotionally challenged individuals, such as trauma patients or autism sufferers, or potentially overcoming language barriers could be another focus, where informative contextual information is relatively easy, but nuanced, idiomatic emotional expression is not. So whilst the emotion data set was used in this study, abstract visualizations as a data communication tool are not limited to this. And the benefits of being able to quickly understand multidimensional dynamic data streams could be used for several information transfer tasks, opening gateways for abstract visualizations as a new non-linguistic way to intake data. And thank you very much.
Thank you, Luke. That's great. So now we'll be open up for questions from the audience for those 2 presenters. So if you have any questions, you can either mute yourself or post your question in the chat. So here we'll have a question from Professor Rachel Jack. Question for Luke. Saying colors can have different meaning in different cultures. So to what extent does this application generalize across different cultures? Or will this be a next step?
So yeah, this is the next step. I haven't looked at cultures yet. One of the considerations that I do need to make is, should a language like this be completely intuitive, or should this be something which participants would have to learn? As a language, you might have to learn how to extract the emotional meaning, and then because of their structure, it is just better at conveying some of these emotional parameters. Whereas, the current study does really just investigate the intuitiveness of these visualizations, and hence it's only looking at the learnability. Whereas really, I want to do some future studies which basically train someone how to understand this emotional information, and then you could potentially learn to understand, what level of information, what sort of bandwidth could you start to receive from these visualizations.
Okay, great, thank you. Great. I have a question for Chana. So in regard to you generated the 3,600 video clips, what exact parameters were you varying in generating those different clips?
Yeah, so we randomly select 1 to 5 action units. So they are different individual face movements that you could generate on the face. And then also for each action unit, which means that each facial movement, we have 7 parameters for its random dynamics. So it has basically the random parameters for amplitude, so how strong the action unit it is activated, but also peak latency, so whether it's early or late in the video, and also the onset, offset, and then acceleration, deceleration, so how fast and how slow in terms of the the dynamic movements. And that's why we need a large space of these, sampling the combination of all these action units and the dynamics.
Okay, and why did you come to that number, say 3,600, with this amount of different combinations that you have?
Yeah, so this is basically a number. If you are kind of familiar with, the traditional psychophysics kind of approach, this is actually a trial number, which is much less than the traditional ones. Like, in terms of sampling different orientation and the length of the object, you need to have basically all the combination, like the possible combination of the stimulus, but you also need to be very careful, like parametrically sampling the space, right? So it's not just, let's say, single peak from 1 to 0, but you need to parametrically sample the space and make sure that you have a even number, of the trials. And this is, so basically we based on the number of trials on make sure that we have all the possible biologically combination of the face movements, but also with enough number of trials to guarantee that they are, after this amount of trials, we will collect the data that will be able to produce a statistically robust model, rather than saying, we generate the model based on this participant only select this action unit for one time.
Okay, I see. Yeah, great. Thank you. Right, okay. I don't think we'll have any further questions from the audience for now. If there are more questions, I will pass those questions to you individually as email messages, and we can get the answers emailed back to the audiences should they have any. Okay, so that.
Yeah, Jacob, I have a question for.
Okay,
John.
yeah, go ahead.
Yeah, so this question is for you. So I saw in your abstract that you talk about the social robots, social agents. So what do you think about these social aspects of the robot, like in terms of this diverse facial expression, for example? Like what are the challenges you can think of?
Yeah, I think one thing that, one continuing challenge in social robotics is that people need to feel that this is natural movements, and in the real research of facial expression, we all know that individual differences and also variation is very important for, let's say, accurate recognize different kinds of pain, but also the variety of the patients. For example, you may have patients from different cultural backgrounds, or they may have different kind of idea of how to express a pain. So all these kind of differences need to be considered when we generate the simulators, right? So because you need to basically trying to make the simulators to present the real scenarios rather than just like one single training of prototype. And then, in the real life, then the simulators may have presented the gap between the real natural variances from the training. So that's why I think the natural variances and also understanding how precise, those dynamics or those patterns in the natural population is very important, and for, the social robotics.
Yeah, excellent. Thanks a lot for that answer.
Thank you.
Yeah.
Okay, do I have any further questions? Right, so if no more questions, then that will sort of conclude our morning session, and we'll go into a lunch break, and we'll be back here at 2:15 p.m. BST. So we'll be back here in about half an hour's time with a technical keynote from Professor Pietro Vadastri to kickstart our afternoon session. And yeah, I will see you guys later.
Thank you, Jacob.